on the quantum supremacy of SYK and operator growth on networks. Jeff, I will give you a 5-minute warning this time.
Thanks, Arthur. Let me just see if this works. Okay, can you see it?
Yeah, yes.
Cool. Great. Well, thank you, Horatio. Let me begin, like the other speakers, and thank Nathan and his team of organizers. I have some vague recollections of what it takes to put together something like Strings. And I must say, this year's meeting has been nothing short of spectacular, and we're not even halfway there yet. So I want to talk today about some work that I'm doing with, some work in progress with some really great collaborators, in particular, Jan Ole, who's a grad student at Autónoma Barcelona, Junho Kim, who's a postdoc at the Institute, Mateo Carrega at CNR Spin, and this project was really driven by Dario Rosa at the Institute for Basic Sciences in Seoul. It also builds on some earlier work by Dario and Mateo, as well as myself and a former student, John Gabriel Hartman, as well as John Schock. All right, so why SYK? Fortunately for me, Grisha Tarnopolsky and Steve Shenker did an excellent job of motivating the SYK model, which has really emerged as a mainstay of the field over the past few years, in part because of its versatility, and not just in high energy physics, but also in condensed matter theory, in many body physics, etc. And today I want to elaborate on yet one more application, if you want, of the SYK model, and that's the idea of quantum batteries. So this is a relatively new application of SYK physics, say, introduced by Dario Rosa and Mateo and their collaborators last year. And this work largely builds on that work and extends it in ways that I'll describe today. Okay, so the next question you might ask is, why batteries? So let me motivate a little bit why I'm thinking about batteries. Here's my country, South Africa. Each of those geotags that you're seeing there represents a town or a zone in the national power grid that doesn't have power. This is not cumulative counting. This is a day in the life, rather, circa February 2021. As our national power supplier institutes rolling blackouts to preserve the national grid. So if, like me, the word load shedding means something to you, it's part of your vocabulary, or let's say you lived through a Texan winter of 2021, then you're probably thinking about batteries too. Seriously though, quantum batteries are a novel idea to test some physics from quantum many-body physics, which may or may not shed some light on issues that we as a community of string theorists care about, like quantum gravity, black holes, etc. Okay, so let me start off then by defining what I'm going to mean by a quantum battery. We're really interested in studying small quantum systems. So a closed quantum battery is going to be, a quantum battery is going to be taken to be a closed, let's say, d-dimensional quantum system with some non-degenerate energy levels and some associated internal or battery Hamiltonian. Just to check, can you see the mouse moving around as well?
Yes.
Great. Okay. So what you see in the picture here is a two-level quantum battery that's spin down, which we'll take to be empty, and spin up, which we'll take to be a full battery, with some difference in the energy levels of, let's say, 2 epsilon, and we'll put this guy in a magnetic field that will be used later. The point here is that we're going to want to deposit and extract energy from the system by some set of cyclic unitary operations. The energy is extracted through some quench protocol, where we take the battery Hamiltonian and add to it some quench Hamiltonian, some quench potential, say, V of t, to give us a driving Hamiltonian. This system will evolve according to the von Neumann equations for the density matrix, which can be solved in terms of the initial condition, rho, and unitaries built from the time-ordered exponential of the driving Hamiltonian. And this, in principle, can correspond to any unitary transformation in the battery's Hilbert space. We're going to be interested in the work that's extracted from the system at some time tau, or work deposited into the system after some time tau, which is given by the difference between trace of rho h naught and the trace of rho of tau h naught. The maximal possible work that I can extract from the system is what's called the ergotropy of the system. Okay, so this is the maximum amount of extractable work optimized over the unitary operations. Okay. So amongst all the possible states of the system, we're going to call a passive state, or an empty battery, is one from which I can't extract any more work. And you can show that some state sigma is a passive state if and only if trace of sigma h naught is less than or equal to trace of sigma of t evolved by unitary operators u h naught. And this must be true for all unitaries u. So given this, any state, let's say rho, possesses a unique passive state, let's call it sigma rho, for which the work extracted, W max, is maximal. And the way we get that state, the way we connect rho to its passive state, is through some set of unitary operations that will rearrange the eigenvalues of rho in non-increasing order. The consequence of this is that the ergotropy, W max, is a bounded function. And this bounding of the ergotropy contains a canonical Gibbs state, omega beta, where beta bar, evaluated at the inverse temperature beta bar, where beta bar is the inverse temperature that's dialed so that the von Neumann entropy of the state rho, S of rho, is equal to S of omega beta bar. Okay. Interestingly, all thermal states are passive states, and specifically for a two-level battery, all passive states are thermal. Okay, but the product of passive states is not necessarily a passive state. This is going to be important in what's going to come, because we're going to try and build batteries from ensembles of batteries. So in particular, if I take some set of products of these unit cells, some set of products of passive states, while the product of passive states is not necessarily a passive state, a completely passive state is one which it is. So the product of sigma rhos is sigma of the product of rhos. Okay. The key point here is that a state is completely passive if and only if it's a thermal state. All right, so suppose we want to take we want to build a battery out of an ensemble of, let's say, n copies of this unit cell of d-dimensional batteries. All right, the global Hamiltonian that we'll construct will just be the sum over the individual cell Hamiltonians. And we're going to assume that the energy structure of each of the constituent cells is the same. Okay, if this is the case, then the question to ask is, can we extract any additional work from the product state until we reach a passive state? Right. the maximum amount of work per copy that we can extract from this quantum system is given by this W max. It's a function of n, goes like 1 over n times the trace of the product of rows minus the passive state corresponding to this times the n copies of the battery Hamiltonian. And for a large ensemble, you can show that the energy of the passive state doesn't differ much from an ensemble of Gibbs states. In particular, as n goes to infinity, this is tightly bound by, the trace of rho h01 minus the trace of omega beta bar h01. So there's a tight bound on just how much energy you can extract from this ensemble. The passive state that's associated to a product is diagonal in the eigenbases of the local Hamiltonian. And so it's a separable state. But in order to connect n products of n copies of this unit cell to its associated passive state, we're going to need at least two-body operations. And these two-body unitaries can be used to extract work from the system, and at every stage, keeping the state in a separable state, the system in a separable state. So optimal work can be extracted from the system without entanglement, but it requires longer times to do so. Okay. On the other hand, if we consider, instead of extracting work from the system, depositing energy into the system, then the deposited energy is simply the opposite of the work extracted. And as long as we're considering closed systems, which we will be in this talk, the two tasks are essentially equivalent. The problem here is that the unitary operations required to be performed on the system require a finite amount of time to be performed. This is a statement of the fact that the Hamiltonian is bounded, and so finite magnitude. So if I have a pure state, let's say psi, and I evolve psi to some other pure state phi by some unitary u that's generated by the driving Hamiltonian, then this time is bounded by this function t of, by this time t of psi and phi, which is given in terms of the distance between the two states in the Hilbert space and the minimum of the time averaged energy and the standard deviation of the driving Hamiltonian. From this, of course, the quantity of interest is going to be the power in the system. So the average power that I'm concerned with here is defined as the ratio between the energy deposited on the battery and the time required to perform the unitary operation. And the instantaneous power I get charging between, the instantaneous power of some unitary that's charging between the state rho and the evolved state rho of t is the time derivative of the work. And this is given by this expression, which importantly contains this commutator between the driving Hamiltonian and the density matrix. So what we want to do here is essentially compare two Hamiltonians. Two configurations of the battery, if you want. One configuration of the battery I get by basically just taking copies of the unit cell, so some local set of batteries in which when I drive the system with the driving Hamiltonian and I deposit energy into the system, I do so individually. And the second is that I can define I can link all the unit cells together to define some lowest energy state G and some highest energy state E of a global battery, in which case the energy deposited onto the battery after time evolution from G to E is just the n times the difference in the associated eigenvalues. So we want to consider the effect of some local driving Hamiltonian versus some global driving Hamiltonian, subject to the constraint that I really only have so much energy to deposit into the system. Here, I'm taking the operator norm, which gives me, which is the largest singular value of h, and since h is a Hermitian operator, this is the same as the largest eigenvalue, and I require that this thing be positive. The result of this is that the collective Hamiltonian that drives G directly to E does so along the shortest path in the space of entangled states, and gives a power advantage n times that of the local Hamiltonian H parallel. So I get a power advantage by coupling all of the unit cells together that I don't get by charging each of the individual cells by themselves. So one way of quantifying this advantage, and in particular the advantage of global driving versus local driving, is through this parameter that is the ratio of the average power of whatever driving process I'm using to the average power of using the local Hamiltonians. And this is the quantity called the quantum advantage. And it characterizes the power of these operations. This guy is typically bounded, and the bounds on it obtain from the kind of constraints that I put on the Hamiltonian. What's going to be important for us as we get to the SYK system is that for a k-local Hamiltonian with k bound k lying between 2 and n, and each unit cell participating in at most m interactions, gamma, the quantum advantage, is bounded by essentially the order of interactions. Specifically, the charging power can't be enhanced if I increase the number of unit cells in the battery, but the order of interactions between the unit cells is an effective resource in this game. Because we're talking about power, if I want to deposit large amounts of power into the system, deposit large amounts of energy over short times, this will necessarily, essentially a statement of the energy-time uncertainty relations, result in large fluctuations in energy, and therefore charging inaccuracies as well as instabilities in the system. One way to overcome these is to consider some system like, let's say, a quantum battery built out of harmonic oscillators in the Gibbs state that are charged through unitary operations. And if I use Gaussian unitary operations like single mode squeezing or combinations of squeezing and displacements, then these are operations that are preserved in the space of such unitaries, and I can essentially mitigate performance against optimization in the system. Another way to do it that's more interesting for us is to build the system using the SYK Hamiltonian. So here, again, let me just remind you that the Sachdev-Yekitaev model is just a quantum mechanical system of n Majoranas with all-to-all random q-body interactions. And that has some rather interesting properties. The property that's most interesting for us is that it is solvable with Gaussian random couplings. The rest, while interesting from the perspective of the dual physics, is not going to play too much of a role in what I have to say today. What I want to do with this SYK Hamiltonian is to use it in a charging protocol. So the charging protocol that we're going to be using is to have some battery Hamiltonian quenched by the SYK Hamiltonian. So this is the driving Hamiltonian that we're going to consider. Lambda of t is a function that's 0 when t is less than 0 or t greater than tau, and it's 1 everywhere in between those two. The stored energy in the system grows until some model-dependent that is to say, what I choose for the quench Hamiltonian, until some model-dependent time scale, say tau star. Then it fluctuates wildly above some average value, E bar, with some model-dependent relative size between the highest energy and the lowest energy level. And this is for a local battery Hamiltonian H0. Okay. What we really want to do here is to compare these SYK batteries that are being driven with an SYK quench Hamiltonian to other models. And one way to make this comparison is to compare the optimal average power, which is a bounded function depending on these two variances. For
you have 5 minutes.
Cool. For H0 and H1, where delta H1 squared corresponds to the charging speed, and delta H0 squared corresponds to the distance traveled in the Hilbert space. Essentially, the quantum advantage in the system corresponds to, sorry, this is ironic, but my battery is about to die. Let me just, let me just adjust that. The quantum advantage corresponds to faster than linear scaling of P of n with n. The genuine quantum advantage, which I'm happy to discuss in more detail later, corresponds to superlinear n scaling of just this term delta of H0 squared, and not the quench Hamiltonian. Okay, so that's what we need to look for to detect a quantum advantage in the system. And in fact, let me go back to this picture. Here's the same energy depositing of the SYK model compared to the SYK battery compared to the many-body battery. And you can see that the difference is quite remarkable. The many-body quantum battery, something like a J1, J2 system, outperforms the spin chain battery significantly, but it still has significant energy fluctuations at early times. The SYK battery does remarkably better. It's got greater precision and stability at all times. It also saturates a larger and faster charge than other batteries. Okay, let me not talk about this here. So what we want to do here is ask how a change of interactions of the quantum system affects the quantum battery properties. So I'm going to talk about the idea of using graph theoretic language, where the SYK model corresponds to a complete hypergraph, and generalize that from a complete hypergraph to a general connected hypergraph. The only thing that changes here is the average value of the Gaussian random couplings includes a factor of the number of edges in the system. And here I want to consider two graph topologies, a circle topology and a star topology. Here, each Majorana is connected with its nearest neighbors, and here a single Majorana, psi n, say, is connected with all the others. In both cases, I'm going to pick the number of edges equal to the number of vertices equal to n, and compute the power, as well as this variance delta H0 squared. And what's remarkable here is that the star graph X model, where the H0 contains just a single Pauli operator, sigma x, outperforms even the standard SYK and SYK quantum batteries. So there's SYK4, here's SYK2, here's the circle graph, which is really horrible as a battery, and here's the star graph. Okay. So let me just say a few words about some analytic approximations to how to compute this power. Essentially, to compute the power, we want to calculate this quantity here, where the overline bar is an average computed over the Gaussian couplings. The fact that I'm averaging over the Gaussian couplings simplifies this commutator quite significantly, but nevertheless still results in a whole slew of nested commutators. And in practice, computing these proliferated nested commutators is quite formidable. But we can do it up to 8 nested commutators, and we get an expression for P8 bar. And we can check this P8 bar against the exact numerical computation. And you see that right up to the maximal charging power, they agree quite well, with significant deviations between the approximation coming from computing these nested Hamiltonians, nested commutators, coming only at late times. Okay, so let me skip this, and I want to talk about a class of particular networks that, or graphs, that I want to put on this SYK model onto. The class is called a small world network, and the small world network is really where we're all sitting in our individual homes and not sitting on in Sao Paulo sipping caipirinhas. This is the small world network that represents flight paths through the world, and really the driver of the virus that we're dealing with at the moment. What we did was to put these quantum batteries on such a small world network, and the key point about the small world network is that it's a network in which there's a large number of cliques or neighborhoods, and a small number of interactions that stem throughout the entire neighborhood. So think about countries and people on international flights that can go across the entire world. The idea here is that you have a small path length in the network and a large amount of clustering. What we did was to calculate a quantity called the Krylov complexity, which will tell us how batteries on these networks compare to typical SYK type batteries. And this is really remarkable. So the main point I want to mention is that for small operators, the SYK2 model, so these are two Majorana fermions, or n Majorana fermions, or two-body interactions, perform significantly better than these small world graphs that are nearly regular graphs. And this corresponds to the fact that this corresponds to the fact that the SYK2 model is not really a scampering system. We know that already. However, when I probe the system with large operators, so when my initial Hamiltonian H0 is a large operator with many Majoranas, say, then the situation is really quite different. And a highly connected graph like SYK2 actually does the job of spreading those operators through the network really well. If, on the other hand, I consider a small world network that's nearly random, then a large number of long-range interactions, then the small world graph works just as well as something like SYK2. This is interesting because such a small world network has far fewer edges than the SYK2 model. So 2n edges versus n squared edges. But the interactions between the vertices in the system, the interactions between the Majoranas, is really quite efficient, enabling the system to spread the original operator out quite far. So let me conclude then with some observations and some open questions. The first is that quantum batteries provide yet another arena to display the power of the SYK model. I'm aware of the pun, and I don't apologize for it. Quantum advantage, this gamma property that we noted, really requires two ingredients. One is sufficiently non-local operators, the H0 that we started off with, and the other is interactions that are able to utilize the non-locality. SYK-like models on graphs provide a versatile set of quantum systems in which we can probe things like thermalization, localization, transitions between integrability and chaos, specifically in the small world model. And for this, I refer you to the work of Xu and Susskind and Swingle, and Garcia, Rosa, Fabalscott, etc., as well as a large body of work by Andy Lucas, and our work with Jean-Gabriel Hoffman and John Schock. And then let me finish with some open questions. The first open question is a very technical one that I didn't get to cover much, but essentially the question is, how tight is this bound on the power of charging power, and consequently, how tight is the bound on the quantum advantage for quantum batteries that are not just defined on a regular lattice, but on general graphs. So Dario Rosa and his student have some work coming out that clarifies this. And then, essentially, because of the statements that I made in terms of the Krylov complexity, operator complexity, I'd like to understand how these results relate to the operator thermalization hypothesis work of Shalom and Zahn and et al. From a couple of years ago. And then finally, given the audience in this meeting, it obviously begs the question, what are, if any, holographic interpretations of these statements? So let me finish by, again, thanking the organizers. And it's a wonderful statement of our community that every year, come hell or high water and pandemics and rain and shine, we get together to celebrate the birthdays of Douglas Stanford and Kristan Jensen, who is our next speaker. Was one of the next speakers who celebrates his birthday today. So I'm glad that the organizers were able to put together such a wonderful birthday conference, and thank you very much for your attention.
Thank you, Jeff. Let's thank him. So we are a little bit over time, but let's have some questions. Well, I see one in the chat, actually, maybe several. So let's see. So the first question was, what happened when you consider a quantum battery is attached to a thermal bath and taking energy out of that, like open quantum system?
Right. So I don't know is the answer. It's a really interesting problem that we're still thinking about.
All right. Let's see. There was another question from Chris Krylova. Does it matter if the graph is oriented or not?
Does it matter if the graph is oriented or not? By oriented, do you mean if I label the edges in some way?
I think so, yeah.
With, let's say, arrows. Yes, I would imagine yes. And you know, one way to think about this is the difference between, let's say, real Majoranas and complex Majoranas in the SYK versus charged versus complex SYK case. So yes, the algebraic graph properties change in that case, and I would imagine that there would be some change, but I haven't really given much thought to it.
So would that just be a specific case if it's oriented? Could you extend it to non-oriented and see what happens?
I'm not sure, to be honest.
Okay. Great.
It's an interesting question.
All right, so I think we're a bit over time, unfortunately. So let's thank Jeff again. All right, so Pedro.
Yeah, thank you. Okay, so we are moving into the black hole discussions for today. So I'm sure they are going to be entertaining for sure. So let me remind people also that if you have more questions for Jeff, maybe the average session where I'm sure we'll discuss lots of SYK would be a good point to follow up on some questions that we did not have time to pose. So let me say a few words that will not count towards the initial 20 minutes of introduction of Netta and Rob. So the idea of these discussions, we have 20 minutes. And these 20 minutes are totally up to Netta and Rob. So for example, they are even going to do something a bit different. They are going to do a bigger block in the beginning, like 15 minutes, and use the remaining part of, say, their last 5 minutes a little bit later into the discussion. So Rob and Netta, please just let me know when you want to use those last 5 minutes or so. And also, in the 30 minutes, please turn on your camera in the 30 minutes of informal discussion if you want to participate. Raise your hand if you want to ask a question. I'll call upon people mostly by order, but also giving slight priority to people that have not asked questions yet. And if you want to ask a question about something that is being discussed right now, just please wave your hand. So And this, I suspect it's going to be particularly important in this session. So some people told me, I know how to clap, I know how to raise my hand, but I don't know how to wave. But it's easy. If you raise your hand, then you just move your hand a little bit and then you'll be waving. So just turn your camera on and we'll be able to see you very well. So I guess that's it. I'll pass it over to Rob and Netta.
Okay, thank you. So Netta and I here lead the discussion, but first we'd like to thank Pedro, Horacio, Nathan, and all the rest of the organizers for doing such a wonderful job bringing us all together for Strings 2021. I'm going to be doing a bit of introduction just to set the stage. Here we see the Penrose diagram for an evaporating black hole. Of course, the marvelous discovery of Hawking's was that when we take into account quantum fluctuations, the black holes actually leak or emit radiation. Of course, the contradiction or the puzzle arises when we take into account the collapse being formed not by a proper star, but by a pure state. So we might have some quantum excitations that are focused to produce a gravitational collapse, form a black hole, and all of the subsequent evolution. However, when we look at the mixed state, eventually the black hole has disappeared, and we're just left with this cloud of radiation on a late time slice, which, as I said, is in a mixed state. It appears to be thermal radiation. Of course, that's in contradiction with the basic tenet of quantum theory, namely unitary time evolution. If we start with a pure state, we should end with a pure state. Of course, the origin of the mixed state can be understood in terms of a pair production process, as Samir mentioned on Tuesday. If we look at the vacuum state near the horizon, what we see are their entangled pairs across the horizon. One of those quanta outside the horizon can escape to infinity and become part of the Hawking cloud. The other pair, or the other quanta in the pair, is trapped behind the horizon and never escapes. Now, Don Page took this into consideration in thinking about what a unitary time evolution should look like. He noted that if we think about the entanglement entropy of the radiation, it starts with 0 when we have no radiation, but as the black hole emits more and more, the entropy simply grows until the black hole disappears here, and at that point, the entropy is capped off. However, if the origin is really this entanglement with the degrees of freedom behind the horizon, then the entropy of the radiation should be bounded by the entropy of the entangling system, namely the degrees of freedom behind the horizon. Those in turn should be bounded by the Bekenstein-Hawking entropy, or the area over 4G of the horizon. And then this is shrinking as the process proceeds, as shown in by the green line. And so what Don realized or argued for was that in a unitary time evolution, the proper description of the entropy should be a rising part, but then in the latter part of the evolution, that should be decreasing, and there should be some kind of hidden correlations between the early radiation and the late radiation. Now, one of the real puzzles is that this turnaround happens around the middle of the process. And so this is when the black hole is still microscopic and we feel we understand, or should understand, all of the physics in play. Now, the exciting progress came about just over 2 years ago now, when these two papers showed us that, in fact, we can calculate for certain models the page curve in a controlled manner. Of course, there's been a lot of activity since then building on this work, and I hope to hear from many of you in the discussion section. But to bring to the fore one of the key ingredients in this new work, it's the idea of the quantum extremal surface, as was featured in Jeff's talk yesterday. Ruin Takiyanagi taught us, in thinking about holographic entanglement entropy, to think about extremal surfaces, namely surfaces that extremize the Bekenstein-Hawking formula over a certain homology class. However, these authors here, including Netta and Aaron in particular, taught us to think about the generalized entropy, where we don't just have this geometric boundary term, but we also take into account the entanglement entropy of the quantum fields on a partial Cauchy slice extending out from that surface to the boundary. Now, when there are a lot of calculations, but when they're all combined together, they can be summarized by this island rule that was as dubbed by our friends here in Princeton. And the idea is that the proper calculation of the entanglement entropy is given by an extremization of the generalized entropy, where we're considering not just the radiation region or the Hawking quanta, but we're also including geometric regions near the black hole, or the so-called islands. And those islands contribute both to the quantum part and to the geometric part here. And so there's a minima here because what comes into play is a competition of saddles for this formula here. At the early times, the island, as Jeff says, is the empty set. There is no island. We're simply doing Hawking's calculation. But then at late times, a large amount of entanglement builds between the radiation and the region behind the horizon, and a new saddle appears with a non-trivial island, and that describes this falling entropy here. And this, as I said, competition of saddles is something we're used to in thinking about holographic entanglement entropy, and it's exactly, in fact, that competition of saddles in certain holographic models that we may hear about later. But it's also been this formula has been justified by new calculations involving replica wormholes, as Steve Shenker reviewed in his talk on Tuesday. And so at that point, I'm going to hand it off to Netta for the second half of our discussion or our presentation.
Thank you. Let's thank Rob while Netta sets up the screen share.
All right, can you all see this?
Yeah, please go ahead.
Great. So again, I want to also thank the organizers and also thank Rob for the first half of this. So as Rob has already reviewed, entropy has done a lot for us on the black hole information front. And so here's a very brief status check. We can put a check mark on deriving the page curve, but we can't really put a check mark on resolving the information paradox. So that's something that we have yet to do. And the purpose of this part of the discussion is, of the prelude to the discussion, is to ask the question or to raise up the point that potentially entropy is not enough. This, of course, is brought up by Lenny Susskind in a somewhat different context of the growing volume of the wormhole in the thermofield double, where he proposed together with others that this is dual to the complexity. And so we could ask at this point, and we would not be the first ones to do so, what is the role of complexity in the information paradox? And really this was discussed already long before these recent developments of the last couple of years, computing the page curve, by Harlow and Hayden, who pointed out that decoding the Hawking radiation is exponentially complex. And this was followed by Aronson and more recently clarified and developed further by Kim, Tang, and Presko. So let me make a few statements that hopefully will not be too controversial. I would say that any full resolution of the information paradox has to explain how to compute the page curve from first principles, from the microscopics, and also has to explain subsequently what Hawking missed. And given Harlow and Hayden's results about exponential complexity and decoding the Hawking radiation, it would seem that exponential complexity is a critical aspect of the information problem. And the ability to access exponentially complex operators, the ability to compute this, appears to be rather crucial in deriving unitarity, since it is part of decoding the Hawking radiation. Now, one lesson we can learn from the past couple of years is that the geometric picture of entropy has been incredibly valuable in making progress on the information paradox. And so we can ask, can it help us also with understanding the complexity? Is there a geometric picture that can help us understand it better? And so in particular, in the context of this reconstruction complexity, there's a very nice paper, so-called The Python's Lunch, by Brown, Gurbian, Pennington, and Susskind. This was referenced in Jeff's talk, so I'll only talk about it briefly. And it's the statement that if you're working with this geometric picture, the geometric avatar of exponential complexity of reconstruction is a non-minimal quantum extremal surface. So here we have a sort of a toy model of a tensor network that is meant to represent a Cauchy slice of the bulk. We have some left and right two boundaries here. And the main takeaway I want to have from this picture is that there are two quantum extremal surfaces here that correspond to two constrictions of the tensor network. And here we have this is the minimal one, and we have tensors that have a smaller number of legs here and a larger number of legs here, which correspond to isometries. And then we have these funny ones that do the opposite. And these are, it's very important, these are post-election, which involve conditioning on an outcome, which is one of the sources of exponential complexity here. So this bulge here in the tensor network is geometrized in this way, on a Cauchy slice of the bulk, where we have some minimal quantum extremal surface and a non-minimal quantum extremal surface here. And that's the reason this is called the Python's lunch, this bulge here in the middle. And similarly, over here, this is just a conformal diagram of the same phenomenon. So the proposal that complexity is proportional to the difference in generalized entropies between the large one here and the smaller one here. And as Jeff mentioned in his talk, you can also argue that non-minimal quantum extremal surfaces are in some sense the only source of exponential complexity in the dictionary, of exponential reconstruction complexity. Now, this is very exciting in the sense that there's a consistency here. So the gravitational path integral calculations tell us that the subdominant saddle corresponds to doing the wrong calculation, the Hawking calculation that gives you a loss of information. And here we see in this geometrization of complexity that if you use the non-minimal quantum extremal surface, you've lost access to the lunch region. You've lost access to the operators that would be exponentially hard to reconstruct and corresponding in particular to the Hawking radiation. So I want to say just one more word about typical states and code subspaces. So just a comment on which quantum extremal surface is minimal or non-minimal, where the quantum extremal surface is that determines what you can reconstruct does depend on the choice of code subspace. And so when the code subspace is very large, less of the bulk is going to admit a state-independent reconstruction. So we may end up having access to progressively less of the lunch if we want to do state-independent reconstruction. So one question that I'd like to bring up for discussion is, what about very large code subspaces? We're talking about typical states. What about typical state arguments for firewalls? So here is just a few questions for the discussion. We're going to go counterclockwise on these. So starting with this one. And we're just going to move along and hope we get to discussing all of them in the time that we have left. So we'll begin with why is semi-classical gravity, and specifically the gravitational path integral, so smart? And we're going to begin with a couple of comments from Chris Akers. So Chris, if you can unmute yourself.
Hey, everybody. Okay, yeah. So what I want to tell you about is this new perspective, or this different perspective. So we want to understand the quantum extremal surface formula. I don't have to motivate why that's important for the information loss paradox. But so far, the usual derivations of it come from the Euclidean gravitational path integral, which are great, but they don't explain everything. So for example, you can use the Euclidean path integral to compute the Bekenstein-Hawking entropy, that S equals A over 4G, but it won't tell you what the microstates are that you're counting. Hence, it would be nice to have a Hilbert space understanding of quantum extremal surfaces in which the microstates are manifest. One approach would be to understand the quantum extremal surface formula as a consequence of the fact that the bulk is embedded into the boundary like a quantum error correcting code. So this is something that was taught to us by Almeridong and Harlow for independent reasons. So applied to this problem, we've actually seen some progress. So this idea was pursued first by Harlow in 2016 in his paper Ryutaki Nagi from Quantum Error Correction. And then it's now being generalized to quantum minimal surfaces. So this is a special case of quantum extremal surfaces where you're applying it to static or time symmetric states. And this will be explained in forthcoming work, probably in about a month, by Jeff Pennington and myself. So some immediate lessons that you get from this. For example, you learn that the area term in the quantum extremal surface formula can be interpreted as the extra entanglement that is needed to encode the bulk into the boundary. And also that this minimality condition, the fact that you're picking like the minimal quantum extremal surface, comes from a certain limited capacity for encoding the bulk into the boundary. Thank you.
All right, thank you very much, Chris. So I think with that, we'll open the discussion on this topic, and then we will move on to the next topic after that. So if you see that if there's a comment you want to make that's more relevant from one of the other questions, then maybe hold on to it until we get there. So
oh, perfect. And yeah, thank you very much. And you did very well on time. So you did reserve time. Yeah.
Hey, let's
thank
go.
You. So.
Can I suggest we go to Daniel to make some comment?
So yeah, I just wanted to say something simple actually related to the question that Netta just brought up. So in quantum field theory, the Euclidean path integral is very straightforwardly related to a trace, a thermal trace in Hilbert space. You know, you just you take the quantum field theory partition function on S1 times some manifold, and you insert complete sets of states going around the S1, and you just very clearly get a trace. But in quantum gravity, and the way we usually do the Euclidean quantum gravity path integral, this is not true, because the thermal circle is allowed to contract. You know, say, for example, at the tip of the Schwarzschild cigar. And that destroys the trace interpretation, or at least the manifest trace interpretation of the Euclidean gravity path integral. And in fact, you know, in special cases where gravity is normalizable, like, you know, pure Einstein gravity in 2+1 dimensions, or pure JT. So since it's normalizable, you can just do canonical quantization, and you get a theory where that Euclidean path integral indeed does not have a statistical. That Euclidean path integral does not have a statistical interpretation in terms of the canonically quantized Hilbert space. On the other hand, in holographic theories, which maybe most of us think are kind of the only theories in sufficiently high numbers of dimensions, then the Euclidean path integral, what it seems to know is it knows about the trace in the holographic dual, right? So it doesn't, you know, if the bulk theory makes sense by itself, then the Euclidean gravity path integral is just kind of a distraction. But if the bulk theory needs some holographic completion, then Euclidean gravity comes into its own and seems to really know that, know about the microstates in the holographic dual theory, even though, you know, from the bulk point of view, it doesn't look like it should. And it's kind of maybe a little bit puzzling. Why should that be true? And so recently, Edgar and I had a paper about this, where we essentially argued that one way to think about it is that the Euclidean path integral is kind of restoring, is the sort of minimal modification of the bulk theory that will restore modular invariance, which in holographic theory is a necessary property of the theory. Thanks.
Okay. I don't know if Chris wants to respond to that at all or make any comment.
I agree with that. Sounds good.
Fine. Okay, I'm Raju Suvret, go for it.
Yeah, I wanted to say a little bit about Rob's initial introduction. So it doesn't quite fit, I think, exactly into Netta's framework. But I think there's something which I think we should bring up and perhaps discuss. And that is that, you know, when the information paradox was first formulated by Hawking, the main assumption he had was this idea of the principle of ignorance, which is that, you know, the Hilbert space factorizes into inside and outside. You can trace over the inside, and so you get a mixed state outside. Now, we know that this is incorrect, but when people first started to talk about the page curve, I think the fact that the Hilbert space doesn't factorize was not appreciated. And so the expectation that you should get a page curve is in fact based on the same assumption that you should have a factorized Hilbert space into inside and outside. And I think now we understand this assumption is incorrect, but, you know, because for historical reasons, we expected a page curve, we now invent, or, you know, we've now come up with many models where the page curve is the right answer. But I think we should, you know, I think appreciate that some of these models are very unlike ordinary gravity. You know, when we talk about the Euclidean path integral, there are points where, you know, gravity switches off at some point. And in higher dimensions, in every case where this calculation has been done, the theory of gravity is actually massive. And so there's a factorization problem. And these are all pathologies of these models that come about because, we're trying to impose the page curve, which is not naturally a gravitational question. So I think there's another way of looking at things, which is that if one recognizes that the Hilbert space doesn't factorize and thinks about how quantum information is localized in gravity, then one would come to the conclusion that the information is always outside. And that wouldn't give us a page curve. But maybe the page curve is not the thing that we should discuss because it leads to all of these other complications in the models where it does emerge.
Thank you, Surat. I don't know if anyone else wants to comment on that, or
I don't see anyone waving. I see
Okay.
Andy. Andy's waving. Andy's waving. Andy's waving.
Okay, Andy, go for it.
I think there is an unambiguous definition of the page curve in asymptotically flat spaces. It's more subtle in anti-de Sitter spaces, but you just have a detector up at infinity, and they measure a quantum state, and if unitarity is restored, then if unitarity holds, then the complete quantum state on Scribe Plus is a pure state. And we measure the state up to some value of retarded time. We always keep very far from the black hole. So we never ask inside or outside. We never need to make that distinction. We just are measuring the radiation that crosses the detector. And in general, that's of course, we have to repeat the measurement many times as usual in quantum mechanics, but that's either, that's some kind of mixed state, and we can just compute its trace rho log rho.
But I think this is precisely the setup that we examined last year. And I think if you look at even at future at Scribe Plus, there is a constraint. And so the Hilbert space, doesn't factorize. And in fact, all the information at Scribe Plus is already available near its past boundary. Now, you could ask for a page curve by, looking only at news operators and throwing out the Bondi mass from the algebra. But then, in fact, it depends on, how much entanglement there is between soft modes and hard modes.
I'm going to agree with you that
all algebra.
I'm going to agree with you that soft modes are important, but in the conventional discussion, those are ignored. And if we're, ignoring those, we just have a bunch of hard gravitons at the Hawking temperature coming out, or whatever else is coming out, and we just compute their correlation.
No, I think you're also ignoring the constrained degrees of freedom in the metric. If you keep track not just of the news operators, but also the Bondi mass.
I am ignoring all that, and I think that's
right, but
that's important. But all of that is assumed in basically every discussion of it.
Okay, but I think if you keep track of the Bondi mass, then I think information, you keep track of the full fine grain entropy in Scribe Plus, then information is already available near its past boundary. It doesn't emerge according to a page curve. One can look at restricted algebras where it does by throwing out some of these things by hand. But
measurements at Scribe Plus don't require you to say what is or isn't inside the black hole.
That's correct. That's correct. But I'm just saying you look at the full algebra at the past boundary of Scribe Plus. So including the ADM mass and the news operators. And then, the entropy is already a constant. So that's what we showed last year in this paper, which I think we also
But if you want to
compute,
want to compute something as a function of time, you can't just look at the past boundary. You have to look at you have to look at a cut of Scribe as a function of time.
Okay, so you could look at a cut of Scribe as a function of time, but if you looked at a cut that extended up to the past boundary, that's an observer who's collecting all the radiation from the start, then that observer just always has the information. You could look at a cut that moves up, so you kind of forget things, and then you might get a page curve. But if you ask, is the information always outside? Then I think the answer is probably it is. You can. There are various ways of discarding information to get a page curve.
Yasunori was not exactly waving, but nodding. So I interpret that as
no. It's not really on that issue. But thanks, Rob and Netta, for the starting discussion, which is beautiful, and I think it's a great start. I want to make some comments. This island and like Python, it's a beautiful progress, which I really enjoyed. And those are based on like a global space-time. You start from like equal time surface, which pass through interior as well. And there you can see islands and so on, QES and so on. But I think it's equally important to start from kind of a unitary, manifestly unitary description, which is essentially boundary description, or if you want to say, Schwarzschild time slice description. And on that description, if you throw in an object, even classically, it doesn't enter horizon, right? It just keeps stacking on this. And then if you turn on Hawking radiation, of course, it's not that surprising that things are unitary because it's like a usual surface because of central dogma people are saying. And then the problem is boiled down. If you start from that, the problem is boiled down to what's the interior of the black hole means. In other words, what analytic extension means in quantum gravity. And even for that, if you throw in some high energy object whose energy is much higher than Hawking temperature, or which is much smaller than horizon, and then you can, or I can show that explicitly the existence of operators whose algebras are exactly the interior operators, and you can construct a local Hamiltonian describing the motion of these guys inside the black hole. If you focus only on these objects, a very, very small code subspace in Netta's point of view, and those are state-dependent operators, but still applies to exponentially many microstates. So E3 C times S Bekenstein Hawking with a C smaller than 1, okay? So very stable operators. So my point is that we need to be clear, I think, on what we want to know, namely to claim that the problem is solved. Because at this level of story or something, we can show it. And the people still saying that the black hole information problem is not solved. So in what sense, when we are convinced that the problem is solved, that we no longer be saying that the black hole has a problem. And for me, so this is the last thing. For me, starting from this unitary picture, the solution is why this particular operator, state-dependent, which is associated with the falling object, is the right operators to use to describe semi-classical physics of the interior of the black hole. And that's to do with what is a classical description, namely quantum measurement. It's a problem of measurement in quantum system with a finite degrees of freedom, because black hole is a finite degrees of freedom. What kind of the operator is right observable in finite system? So it's same as a cosmology. And then I think it's a clearly, completely black hole information is solved. And that's not the one we are interested in the other way, starting from global picture, like island. And then the question, equivalent question, but in the other way, is that what's the wormhole, what's the ensemble, what's the quantum state, if you want. So these are, of course, starting point is different, so question is different, but we want to be clear what we want to know and when we claim that the problem is solved. Otherwise, it's like, yeah, that's the only thing I just wanted to say.
So who would like to address this? Daniel?
I wanted to discuss a little bit more with what Suvrat said, because I think it's worth discussing a little more. So if you think about a small black hole in ADS CFT, so I believe that the analog of, there's an analog of what Suvrat said in ADS, which is if you make a small black hole and then you let it evaporate, if you compute the entropy of all the operators in the dual CFT as a function of time, you get a flat page curve because the dual CFT knows everything, both the radiation and the black hole. And so I think similarly in flat space, it's true that if you think, we don't know what it is, but we can imagine there's some microscopic holographic description of flat space, living probably at null infinity or something like that. And if you include all the operators, and you allow yourself to make arbitrary measurements, then the statement of holography, of course, is that you can learn everything. So there's no natural split into the stuff that's in the radiation and the stuff that's still in the black hole, at the level of computing the entropy of all the operators. So it's only when you restrict yourself in some way, you don't let yourself measure everything in a holographic theory, that you can hope to learn about some subregion in the bulk. And I think that, that's clearly true in ADS, and flat space I understand much less well, but I guess it's true there too.
Can I ask you, Daniel, then in some sense, I'm doing an experiment when I'm building these models of coupling a bath to the ADS space. What's the extra coupling or what's the extra experiment I have to do to get the information out?
What, so you mean like in the calculations of Pennington and Almeri, Engelhardt, Merrill, and Maxwell? Yeah, so I mean, so there you're literally, I mean, there the holographic theory is not everything, right? Because you've coupled it to some external system, so the stuff, information really is getting out. But that's not happening. Right,
but I can think of that as being the experimenter, and I'm probing my system, the CFT or the defect, and I'm pulling information out. And I know Subrat wants to say something, but I don't know if Daniel wants to.
Well, I don't see a contradiction with what you're saying, Rob. I mean,
okay.
To do the page curve, you have to split the system into the part that's still got the black hole and the part that's got the radiation. And if your rules for computing the page curve don't involve that split, then I suspect you're going to get a flat page curve.
And in flat space, there's a very natural way to do that split. You take a cut of scry. All of scry has a pure state. You have take a cut of scry, which corresponds to some retarded time. And you have the quantum state before and after that. And those will be entangled because late time radiation is entangled with early time radiation. So in flat space, there is a canonical way to define a page curve.
So I think I agree with that, but I think
ADS, we have a pure state at every moment of time.
So Andy, I agree with that, but I think Subrat is not going to agree with that.
Yeah, so let's go back to Subrat.
Okay, so let me just say one thing about what Rob said. I think it's true, of course, if you make a division in the space by coupling the system to a bath, you will get a page curve. And that's because, what you're asking is you have a holographic system, you coupled it to some bath, and then you're asking a non-gravitational question about how information flows. But I think one thing that I think one should appreciate is that these couplings introduce various pathologies in the model. For instance, one thing we haven't discussed is that the graviton always picks up a mass in higher dimensions. So these are not really realistic models of black holes. But going back,
can I just interject? The question I'm asking is, you're saying the information is there at the boundary. By adding some extra couplings, can I extract that information into my bath or into my experimental system?
Right. So I think what you did is you forgot about the constrained degrees of freedom because you switched off gravity at some interface. There's some, beyond some point, there's some degrees of freedom. The constraints don't apply anymore. So you threw away some information. And that's how you got a page curve, because you're systematically throwing away information. That's why.
But can I extract that information was the question, though. Can I?
Yeah, you probably can. Yeah.
Okay.
So, Subrat, if we actually build a black hole and we let it evaporate and we feed the stuff that comes out into a quantum computer, what do you think we're going to see for the entropy?
I think that's a great question. In fact, it's what you asked earlier. We could have said the same thing by holography about this hard disk in front of me, right? I could say, by making measurements, I could read the hard disk. But of course, that's not how I read it. And that's because in usual non-gravitational systems, there's a hierarchy of difficulty. You can measure all operators, and that's something which is controlled by n Planck. And then there's the entropy of the system itself. And you can separate them by some significant amount. But I think the question of the small black hole example, which is absolutely right that you mentioned, shows, in the case of gravity, you don't have this separation. The entropy is also controlled by n Planck. So you try and make quantum gravity effects very weak, and the entropy goes off to infinity as well. So there might be a reason that there might not be a meaningful separation between this constrained information, which takes everything outside, and you somehow want to ignore some amount of information, and maybe there's no meaningful way to do that in gravity.
It might be a little bit approximate, but I mean, I really want to pin you down. If you really think if we do this and we measure, we feed the photon, they're just photons and gravitons and whatever. And I don't know what a beam splitter for a graviton looks like, but if we pretend that we could do that, right, and we do some exponential, complicated measurement, or even just the swap test, or I don't know what, to compute the entropy, you think we're not going to see it go up, and you really think it's?
Yeah, I think I'm happy to be pinned down. I think if you measure all components of the metric, like you measure the Riemann tensor and extract, then I think you will not see it go up. And at the level where you start seeing, you have enough accuracy to start seeing the page curve go down, which is e to the minus s, I think you'll find that you always have the information. Not that you don't have the information for some time, that you started having it after some time.
I have a suggestion, just so that we don't stay within the same topic forever. I think that it would be nice to hear from Nicholas and Henry, because they did not participate yet in this discussion.
Yeah, I was going to hand it to Henry. He's made a special effort to get up early for us. So why don't we?
Okay, so let's go to Henry and then Nicholas.
I think Samir and Nick have had their hands up for longer, and and I think I'd be very happy to follow them because.
Go ahead, Henry.
Oh, okay. Yeah. So I wanted to say that I think we're confusing things by trying to impose our desires on the sort of new calculations of the page curve and everything we learn about ADS-CFT and so forth is obviously extremely useful. But I think that we're trying to sort of fit the new page curve calculations into that framework without just looking at what the calculations are telling us and taking them at face value. And there's a very pedestrian interpretation of all of these calculations where it's a purely Lorentzian interpretation of the thing. There's no mysterious non-locality where we have to talk about the island being part of the radiation and having some non-local map between them. We have microstates already. They're just the states that we already have by throwing some matter in to create a black hole. It's just, it has some, the side effect of having super selection sectors or ensembles and so forth. But there's a relatively pedestrian and straightforward change to our definition of the theory of gravity that is a change to what Hawking would have told us, but in which information as measured by observers doing repeated experiments comes out, and there's no extra mystery in there. There's a second question of how that's related to something like string theory, and when we have a full theory of quantum gravity, which I think we can make a lot of progress on. I think there's a lot of connection between the two, but I think it's important to say, first of all, and I'd be interested to see if people accept this, that if you just take the gravitational path integral by itself, without any other ingredients, there's a consistent interpretation where measurements see energy coming out, but there's super selection sectors or ensembles, and this is a perfectly self-consistent interpretation of everything we know, where there's not very much mystery left over.
Henry, let me just ask you. Wouldn't you say that this is still a bit of a black box, that you just sort of issued a bunch of instructions? I mean, why should we be computing the entropy in this way? Why should this object give us the entropy? I agree with a lot of what you're saying, but I don't necessarily agree with the fact that there's no mystery left over. Why are we using the gravitational path integral?
So, well, okay, so maybe this is another point, is that people are often saying this is the kind of mystery and smartness of the Euclidean gravity path integral, which is certainly the way that it was originally thought about and written down. But I think neither of those things are necessary. It's neither Euclidean. There's a purely Lorentzian way of describing the whole thing. And it's the standard way you would do a Lorentzian real-time dynamics with the slight modification that you're summing over metrics. And I think there's also, you could describe it in canonical language as well. But, so I don't think either of these things are really necessary. And it's just the question of we're doing is asking, you're doing standard calculations of expectation values of operators. Expectation values of operators provide you boundary conditions for the path integral, and you calculate and it gives you an answer. And I think it gives you answers that are consistent with one another. So the page curve calculations are computing what is the expectation value of a swap operator acting on many black holes. And I think all the answers you get so far seem to be consistent, if you take that point of view seriously.
Tom was waving his hand. Tom, do you want to?
Yeah, I want to respond to that comment. I think I disagree with this picture. I don't think there's a controlled calculation that suggests super selection sectors in a theory coupled to matter. There may be in JT gravity in 2 dimensions with no matter, but beyond that example, I don't think there's really a controlled calculation like this. And a related fact is that I don't think you can think of the microstates as the incoming, as the different states of the incoming matter. I think people tried for a long time to understand the microstates that way, and it never really worked. So I think I disagree there. I think part of what we have to be really careful about is always saying, with every calculation, always saying in what regime we think that it's valid. and part of what Hawking did wrong was presumably not making that distinction.
I think I won't disagree that there's a really sharp, well-controlled example where, say, we have a factorization problem in four-dimensional Einstein gravity. I think that the double cone comes close, but I think maybe I'm saying something slightly weaker, is that all the calculations that we do have, including that of a page curve, are all there is a sensible, consistent interpretation that doesn't involve any sort of extra non-locality and so forth. And then the second point about counting, about using the black holes formed from collapse as microstates. Okay, so these are not energy eigenstates. They're not microstates in that sense, but they populate the Hilbert space. And of course, the very, very old idea is that these populate the Hilbert space, but they overcount. And that's, of course, you have a very large interior, you can populate it with many, many modes, but these things should not all be linearly independent. And islands, roughly speaking, gives you a way to account for that overcounting. And we certainly don't understand all the details, but I think there's at least, there's a self-consistent picture there. And with some work to understand that, I think that's the counting works, that the equivalences you get between states by including islands in computing in a product between these different states is enough to account for the proper counting.
I see that Daniel is waving, but I really think it would be nice to also give.
Yeah, I was going to turn it.
We should go to.
I think it would be nice to have Nicholas.
Nick, go for it.
So, thank you. Yeah. So I understand that the island prescription doesn't give a mechanism. That I understand, and as Netta nicely summarized, it doesn't. But one thing you should be able to answer, which I'd like a straight answer to, is in the process by which the information gets out of the black hole. Is it non-local in the radical sense? Now, there's a lot of imprecision in the language of non-local. There's non-local of entangled pairs. That's standard non-radical stuff. The radical non-locality is when you actually have a non-local Hamiltonian. And I believe that the information, if you're going to argue that it gets out from the island, in this island paradigm, it has to involve a non-local Hamiltonian if you assume there's a smooth horizon. So the question is does it involve radical non-locality in the sense of a non-local Hamiltonian evolution? And if you say no, how do you get around the small corrections theorem if you also insist on a smooth horizon?
So Tom is waving, yeah?
Oh, very cool.
I just want to ask a question before we get into that discussion, a question for you, which is, how do you even define local or non-local in a non-perturbative theory of quantum gravity? How can we ask if the exact theory is local? What does that question even mean?
Well, I can go to a big astrophysical black hole and I can take my meters a large distance away and ask whether there are non-local correlations between this. I mean, by hiding behind the screen of a quantum theory of gravity, you're neglecting the fact that you can make macroscopic black holes and you can measure stuff.
But if that's your definition of local, why do you expect it to be local? Wouldn't the non-perturbative theory have non-perturbatively small commutators at space-like separation?
Yeah, but I think that kind of thing is covered by the small corrections theorem. I just want to know how the information that fell into the black hole gets out if it's not by some non-local Hamiltonian evolution. I think that's a relatively clear question. You have some information that's separated by megaparsecs. How does it get across megaparsecs? I think it's a reasonable question. I think it's a well-defined question.
Ed is waving.
Well, I think we could try to answer Nick's question as follows. Even before the page time, the state of the outgoing radiation was extremely complex, but it doesn't contain any information about the black hole. After this page time, the state is also extremely complex, but it has a simple description of a bipartite state, including the island. But the island, including the island, is a way to give a simple description. But you could simply say that you have the state of the radiation, which
Yeah, but that radiation halfway through the page time, that radiation is, far across the universe.
There's no.
And so for that state to evolve into this rather simpler state, I assume requires some kind of bilocal Hamiltonian.
There's nothing funny that happens in the evolution of the radiation state when you cross the page time. The only thing which is funny is more a mathematical fact than a physical fact. That as elucidated, as explained to us by Page, a state of more than half contains information when it didn't contain information with less than half.
I'm not sure I understand the comment.
So at this point, we asked someone else to prepare a slide. So I'm going to pitch to Dominic.
I just want to say one more sentence. Nothing. I believe the answer to Nick's question is that nothing special happens that has to be explained by a local or non-local Hamiltonian.
But sorry. It's not true if you choose a global slice, you have to have some crazy non-locality, right? Because you still have foreign object and the radiation. It's clear that you have to.
Right, Dominic?
Okay. Yeah, thanks. So I don't know if this is a good way of like going on to talking about double holography, but it also kind of touches on stuff that's been discussed now. So yeah, maybe let me just make a hopefully somewhat controversial statement to some people, namely that double holography, which is really like I would say the only really good model we have for higher dimensional quantum gravity, including islands, the double holography suggests that in the semi-classical approximation, information about the interior of the black hole is really not accessible from the radiation, but that there's a quantum gravitational, say, reorganization of the degrees of freedom where it is. So we really have a duality. So let me try to give you the basic idea. If we consider like a standard doubly holographic setup, so we take vacuum ADS, look at it from like Rindler coordinates, we introduce an end-of-the-world brane, which cuts off part of the asymptotic boundary. Then in double holography, we can either describe the system in what's called the boundary perspective here on the left, where it's dual to BCFTs, which live on the asymptotic boundary in the thermofield double. And let's think of this as sort of quantum gravity. Or in double holography, thus double, we can take the brane perspective. Namely, we say that the dual theory lives on the asymptotic boundary union the brane, and that's sort of like displayed here on the right, and this really plays the role of semi-classical gravity. And it does so because the brane, so the green line here, is a dynamical space-time with gravity, which contains, in that particular case, an eternal black hole, which at least naively suffers an information paradox. So the argument we do to produce a unitary page curve is the following. We consider the region A, say on the left, and we compute its von Neumann entropy using the RT formula. Now, initially, it crosses the horizon in the bulk and it grows, but after the page time, the correct RT surface connects to the brane, and it's also shown on the left. And that makes the entropy growth stop, and as a result, we get a page curve. The point is that this computation is really done in the boundary perspective, in the left description, and not done in the right description, this brane perspective. But this is where we have the information paradox. And the point is, or the point I want to make is that one can argue in details for those who are interested on the reference down on the slide, that on the right-hand side, we really shouldn't allow the RT surface to just randomly end on the brane, but we should use the usual homology constraint, where we sort of need to pick boundary regions, and we just treat the brane as the usual asymptotic boundary. Now, if we do this, what's the resulting picture? It is that the Neumann entropies of the regions A in the boundary and the brane perspective, they are different after the page time at least. So in the brane perspective, the von Neumann entropy just of region A, so just of the radiation, even computed using RT, just grows without bound. And that's just like you would naively see in semi-classical gravity. And that's possible because the brane perspective is a particular reorganization of degrees of freedom in the boundary perspective. And we can in fact study this reorganization using double holography really nicely because both descriptions share the bulk. And so the particular point here I want to make is that in the brane perspective, the entanglement wedge of A's on the right really never comes close to the brane even after the page time. And so in other words, on the right, the region A cannot be used to reconstruct the island or black hole interior or what have you. This is really only possible in a sort of quantum gravitational formulation
like the brain perspective on the left, which doesn't have like an obvious black hole interior. Okay, they were my comments, so I hope they spark some thoughts or comments or other ideas of what one can do with double holography.
Yes, and
yeah. I like this very much, by the way. I think this is quite beautiful. Congratulations. But my question is that this picture seems to be quite, so what's the point of a double holography? I think the key is what I've been saying is that essentially BCFT, that's the exterior view, like stretched horizon is just the endpoint. And then you have a brain, that's the interior. Okay? So this brain picture is interior. So essentially this BCFT versus this boundary becoming brain, gravitating brain, that's the interior of the black hole. That's, I think, a model of exterior view versus infolding view. So of course, double holography helps in a sense of calculating using Ryutaka-Yanagi and so on, but that's a secondary to be. In some sense, it's a technical, it's beautiful, but essence is this first duality. Do you agree with that?
Yeah, no, I agree with it, but I think that double holography adds something very important there.
Of course.
Namely that we can now study this, right?
Exactly.
So,
that's what I think, yes.
I didn't have time to comment on this, but for example, if you look at the paper or if you remember the slides, and if you sort of combine, well, if you read the paper, you'll see there's like actually a really nice connection with what Netta said. You can see all your extremal surfaces. You can see the outermost extremal surfaces, which sort of tells you which operators are going to be simple, which are going to be complex. And you can study how operators inside or outside the black hole are related in those two perspectives. And for example, in particular, you can argue that the semi-classical perspective is a reorganization of quantum gravitational degrees of freedom, but it really looks like coarse graining, at least outside the black hole.
Exactly. My claim is that in your double holography case, you can use a holography language to do this. That's great. But I'm claiming that you can do even without using holography language. If you carefully look at like hard energy mode and a soft mode, which is related with the soft hair of Landy, and then you just assume the chaotic dynamics plus low energy universality. And then you know that all the coefficient, if you expand in a basis state, is just a Gaussian distributed. That's enough to extract exactly the same physical information. But the language of the holography is quite beautiful, of course.
Let me say something. There are many people. Actually, I want to. Sorry, Rob.
It was good. I would ask your indulgence, and yeah, we'll let Samir talk, and then we'll wrap up. Is that okay, Pedro?
I was precisely going to say that people don't have to worry because we don't need to wrap up because we are going very well, so we can continue. I was precisely going to say that we can be relaxed and go on a little bit longer.
Sure.
But,
okay. Yeah. Samir, why don't you? You've been waiting patiently. You've even turned your camera on now. I'm sure you're. Samir, go for it. Oh, you're still on mute. Oh, there you are.
There we go. Yeah. Thanks for letting me talk here. I just want to continue on with the point that Nick was making, which I think is really crucial here. I have actually been reading a lot of these papers over the past 1.5 years, and I just want to emphasize once again very strongly, in none of them does the page curve actually come down unless either explicitly or implicitly you assume that there is non-local physics, which right now we have not seen directly in string theory. And I have seen 3 kinds of non-local physics being assumed, and I just want people to comment on that after I state them that that's what they actually want. Either it could be something like baby universes disconnect and then they can reconnect somewhere else, okay? Or they can have like non-local identification of bits, like bits at infinity are not distinct from bits in the black hole like Papadopoulos Raju. Or they can be actual Hamiltonian interactions. If you flip a spin at infinity, you can flip a spin inside the black hole and extract information, like sometimes Juan says how you can extract things from inside a black hole. If you do not actually have any of this, but just like, I'm talking about the exact theory here, okay? You can make some approximation, I'm talking the exact theory. If you have none of these, which you explicitly introduced in your exact theory, the page curve is not coming down in any of these papers. Okay, so I just wanted to emphasize that I want to get some reactions, and that's what the small correction theorem tells you. As Nick was saying, if you assume a smooth horizon, the page curve is not going to come down. A smooth horizon to any approximation in the semi-classical way, page curve will not come down, but then these non-local things can do anything, and they can bring it down. So Daniel was also talking about non-local things, one of these the day before yesterday, and I would like to know what kind of non-local things do people have in mind, that what kind of interaction do they think they have postulating in gravity, which would not be part of our normal way of thinking if we just assume that something is happening in the black hole, but once particles leave, they're just like ordinary flat space quantum field theory. What other kinds of non-local things do people have in mind? Because without that, the page curve is not coming down. That was my question.
Eva, why don't... Oh.
So sorry, Rob.
Well, Eva was waving. I also saw Suvrat. But
exactly
Eva,
what I was going to suggest, yeah.
Okay, I hadn't intended to participate in any debates today, but let me just say one piece of just a factual input, which may or may not, how far this goes is up to discussion. There are non-localities in string theory. They're causal. They're consistent with the usual I epsilon. These are the things anticipated by Susskind years ago, and they are strongest in the longitudinal direction defined by the direction of relative motion of, say, a detector of an early infaller in the black hole, and the scale of that along the let's call it the x plus direction up the horizon is delta x plus is p plus of the detector in the local Lorentz frame divided by p squared plus f squared of the detector. So this is just this was a prediction of Susskind's light cone gauge calculations, and we bothered to check it in the S matrix with long calculations. So it does lead to some information recovery up the horizon, which is perfectly causal. How far that goes, I don't know, but extended objects are a key part of all our higher dimensional theories of quantum gravity, at least in the limits of string theory that we know. And in the context of singularity resolution, there are cases where extended objects matter. They enter before Planckian effects. And when they do, they have to be incorporated first. So, Samir, it's not correct to say there's no calculations involving non-local effects. I'm certainly not claiming victory on this whole problem, but I think that one should do due diligence with these things and incorporate the effects in the order that they appear.
Eva, I'm totally with you that there can be very much brane or string effects in the region where the black hole is. I was talking about the fact that these papers which came to bring the page curve down, they need non-local effects across arbitrarily long distances from the black hole to where the radiation is. Anything you do inside the region 2m, 4m is not going to bring the page curve down by these methods. For that, you need the fuzzball when the horizon is gone, no semi-classical approximation.
Okay, again, I'll just say in the Hayden-Preskel thing where you send something in, you ask, can you get the information out of that thing you sent in? The answer was, at least in part, yes, there's information available from this longitudinal effect. I'm not making any claims that that solves the whole problem, but I think it's a very concrete thing. So I just wanted to enter it into the discussion, again, making no stronger claims than that. Sorry to interrupt you, Samir, but I think these are facts, so I'm just going to stop there.
Suvrat, you were waving your hand. Suvrat?
Yeah, sorry. Yeah, I just wanted to say, Samir, I think there's a much simpler explanation for this. And Giddings and Donnelly have already computed in perturbation theory and gravity these commutators at space-like separation. And they just have to do with the fact that, if you insert energy at one point, you have to modify the metric far away. And that's a commutator that's suppressed by L Planck over the distance scale. And that's just there. It's there as part of semi-classical gravity. So it's certainly there as part of string theory. And one may not like it, but it's there. This is not the kind of thing that's easy to see in the S matrix because, this is the degree of freedom that's constrained. So it's not a dynamical degree of freedom of the graviton. But it is precisely the kind of non-locality you need for information to get out. And, so gravity that way is just different from local quantum field theories. And as Daniel said, that's what we see also in holography. And, one can't just rule this out by fiat. And if one doesn't, then, then we don't have a small corrections theorem any longer.
So could I ask you, Suvrat, I didn't want to rule that out, but I was saying that if you have any effect that falls off with distance, it's not going to help you. So I think you were also talking about effects that don't follow for distance in terms of your local non-local identification of bits. So I was trying to ask you about that.
No, I think if the radiation that's coming out is affected by, if the point is the description of the Hilbert space as a result of, these effects is just not that of n qubits, of which 2 of which have got separated. And the small corrections theorem starts with the description of the Hilbert space and then says, small corrections can't fix it. But that description is just not correct. And that's because, the description is in terms of some other degrees of freedom, where you have to have this identification. I think these effects, I don't think there's any contradiction. One can show that these effects follow from, an examination of the constraints of the theory. So one doesn't even need to do some very fancy string theoretic computation. They're just there already in gravity, and you can't avoid them.
I'm actually going to go to Dominic. I think he was Dominic.
Yeah, I just want to briefly comment on what Samir said, right? And just again point out that I think all this island stuff suggests that it's really like holographic duality. Like you can ADS CFT, you can write an operator on the boundary, which might be very complex, but it creates some excitation in the middle of the bulk, although from the bulk point of view, the dual CFT where you apply this operator is at infinity, right? And now you could say, well, is there some non-locality going on? Is there like a Hamiltonian which connects, I don't know, the central point of ADS to the boundary? But no, the story is that those are two complementary, like dual descriptions. And you do something to one description, and in the other description, you, I don't know, apply a complex operator, and in the other description, something pops up in the middle of ADS space. So I think,
Can I ask for a clarification of that? Can I just ask for a clarification on that? Because people often say that ADS CFT shows non-locality, so there can be non-locality elsewhere also. But it looks very different to me, and that's why I want the clarification. In ADS CFT, the CFT is local, the gravity is local. The map from one to the other appears non-local, but that makes sense because if you integrate out the radial direction, things look non-local. But now we are asking about non-locality in just one theory, gravity, and across arbitrary separations, something at one place and something on Mars. And I just want to know if you really mean that there is non-locality in gravity itself, something that I have not consciously incorporated by thinking about gravity, and how I learned that from ADS CFT, because I don't learn that from ADS CFT. So that's why I'm confused.
Right. Let me just very briefly say, I think that precisely those doubly holographic models precisely show this. And they're sort of helpful in the way that you have, the only thing you really need is standard ADS CFT duality with a bit of brains. And this non-locality sort of in the, what do you say, one theory. So it's a d-dimensional theory. You can just understand as sort of the usual story in the d+1 dimensional bulk.
So
you actually don't need double holography, right? Again, so
no, it's just a tool, right? Just
yes,
pedagogical tool.
I just wanted to make sure that double holography is not the crucial part.
So I'm going to apologize to Nick and Daniel that I'm going to put you on hold for a second, because we had to close the discussion, this is in the end, but we had a poll, and I'm not sure if Pedro or Netta is in control of that, but I'm going to. Okay,
but I do want to say we have a few minutes after that, so we will get
to
Daniel, I think. Yeah. All right. Please vote.
Well, yeah, I hope you're all seeing this poll.
Yeah.
Just wanted to do a quick summary, see where the audience is.
I don't know. It's not allowed.
No, it's not. It's not an option on purpose. You got to commit to something.
Your Bayesian prior, is it greater or less than 50%?
Yeah.
Does 2 require that we actually acknowledge a firewall makes any sense whatsoever?
You're welcome to not.
You mean the Boer
no on that
one? The Boer vacuum, perhaps.
It would have been nice if maybe was a possible answer to some of these questions.
Oh, no,
everyone will pick maybe. That's no fun.
It feels very, I don't know, okay.
Which was considered, but.
I really object to this. Just forcing us to, it's like.
Go on, Andy, stake out territory. It doesn't, haven't stopped doing it.
I want to stake out territory, but my territory is not an option.
Exactly, I have that problem too. So just annoy other people with your responses then.
We're still gaining a lot of responses.
But Rob, I just want to make a quick comment. I still don't think I have had a response to a real response to my question. Ed told me something which is interesting, but it doesn't tell me whether that state is reached by a non-local interaction. So I'd like to actually know whether this recovery of information involves non-local interactions in these formalisms. I don't want to answer that question.
Okay.
I think it's also Samir's question.
I couldn't tell if Nick was asking me for my opinion, but
Edward, why don't you go ahead?
I wanted to follow up. I wanted to follow up because you described a state of affairs, which I want to know how it got that way.
I think the answer is that there's absolutely nothing that happens to the state when you cross the page time. The island story is a convenient way to give a simpler description of the complex state of the radiation. But the state of the radiation has not changed in any fashion when you cross the page time. It was a very complex state of many quanta. After the page time, it's a very complex state of slightly more quanta. The only difference is that after the page time and not before, as shown by Page, it contains information about the initial state from which the black hole formed.
Okay, how does that differ from the discussion of a piece of coal, which is halfway through the burning process, information starts to come out? We know from local quantum field that we know from local calculations in quantum field theory around a black hole that it's not a piece of coal, unless you believe the fuzzball program.
Well, there's only one difference from the piece of coal, which is that for the piece of coal after the page time, there isn't a simple semi-classical formula for description of the state. So the island formula is a simplification that's absent.
Fair enough, but that doesn't necessarily mean it's right or an advantage.
Well, I think the only place that non-locality arises is that if you try to make an extremely complex measurement of the outgoing state, which is necessary in order to test experimentally some of these claims, a sufficiently complex measurement, then you can't ignore the fact that a sufficiently complex measurement has a non-classical effect on the geometry. But that wasn't part of the question you asked. The question you asked was, let me finish the sentence. Sure. The question you asked was, what happens to the state when we cross the page time? And the answer to that question is nothing.
No. My question I asked was, is there intrinsic strong non-locality of a Hamiltonian form in the way in which information gets out of the black hole using in this island scenario?
The answer, I believe the answer is no.
Okay, then how do you get so the follow-up then is, if you said the answer is no, how do you get around the small corrections theorem?
Well, it's going to be hard to give a complete answer in the available time, but I think where a paradox with locality actually arises is when we try to think through what's involved in the experiment that would test some of these claims, showing that the state of the radiation is not thermal by an extraordinarily complex measurement. I think we have to accept the fact that if we make this extraordinarily complex measurement, the measurement will change the semi-classical picture of the geometry. I believe that's the only point at which something funny is going to happen. So to recapitulate my answer to your question, the answer to the question of what happens, what was the interaction that occurred when we crossed the page time, is that absolutely nothing happens.
That wasn't actually my question. My question was about the non-locality or intrinsic non-locality needed to get the information out, and the presumption that often goes into these discussions that this is a smooth horizon.
Where the non-locality would arise is when we try to carry out in practice the operation involved in proving that the outgoing state contains the information. That involves an extremely complex measurement, which probably changes the space-time geometry.
So is the word here extremely complex code for an extremely small correction to the state away from thermal, or is it something else?
So can I say something?
Can I address the question
Samir was waving his hand.
I don't know. Can I address Nick's question?
I think I would suggest that at this moment I think we should thank Rob and Netta. We can continue, but we need to test the share screen. So please continue, but I will be in the chat asking people to share the screen. So let's please thank Rob and Netta for this beautiful discussion and everyone else. And yeah, please feel free to make some more comments, but now I'll be in the chat chatting with people, asking them to share the screen as well. Don't be distracted by that, please.
Nick, I just want to tell you one thing, because it seems like I understand your question, at least, Samuel. And that depends on kind of gauge, if you want to say it, or dual, you want to use language of the Dominic, or whatever, the distant picture. If you take short pseudo slice type description, then you don't need that kind of locality, non-locality you were talking about, because information is stored in the horizon and coming back, and no interior a priori, right? So there's no locality. But if you want to take a slice, like a nice slice, which going to interior and both exterior and interior, which pass through late Hawking radiation and fallen object, both of them, it's clearly you need a locality, otherwise quantum no cloning theorem is violated. So if you want to do that kind of description, yes, a huge non-locality is needed, and that avoids a small correction theorem. And the small correction theorem was formulated in that.
That's why I kind of wanted that clear statement. But yeah, absolutely. If you want to go the non-local Hamiltonian route, you can solve the problem. That's all. But
can I say something? There's no non-local Hamiltonian being introduced by hand. It is, I mean,
there's a lot of wishful.
Can I say something? No. Sorry. Can I say? I think the small correction theorem starts by assuming a factorized Hilbert space, and there's a very simple challenge, which is that if you feel that a factorized Hilbert space is the right description, can we in perturbative gravity write down one local gauge invariant operator which just commutes with everything around it? We can try this in ADS-CFT, and I think the answer is we can't write down such an operator. I mean, so the small correction theorem starts with that description and then says, this can't, if you make small corrections to this description, it won't work. But that's just not the right description of the Hilbert space, and it's not some non-local Hamiltonian we're putting in by hand. It's just part already of the structure of gravity. I mean, that's what Daniel was saying earlier as well. I mean, Samir was asking how you see this from ADS-CFT, but I think, you do.
I just say I agree. Yes.
I mean, sorry, I just want to say very, very briefly. I mean, this issue has nothing to do with black holes a priori. I mean, I think you just first think about a spin in the center of the bulk in ADS-CFT in vacuum and trying to read that spin from the boundary CFT. So it's true that there's a measurement that you can do in the boundary CFT at t equals 0 that tells you whether the spin is up or down. And that appears to violate causality from the bulk point of view. But like Edward said, if you think about the experiment where somebody measures that operator at t equals 0, it's just one that doesn't preserve the semi-classical picture of the bulk. And so once we've accepted that we can violate locality with a complicated measurement at a scale which is infinity times the ADS radius, I don't see why it should be so controversial in other situations.
Sorry, I think we need to stop now.
Can I just ask Juan to give his comment? He's been waiting for.
Okay, go ahead, Juan.
I just wanted to mention that when we talk about these complicated measurements, we should not neglect the space-time that the complicated measure generates. So it might be that to do the complicated measurement, you need to do a sequence of simple operations, and that will create its own space-time. So I think this question of locality is intertwined with this idea. So it might be that you generate a copy of the system and there is a new space-time and it gets connected through a wormhole to the interior and so on. And that might be the description. So this idea that when we act with a complex operation, there is some magic that happens might not be the right description. It might be that we need to explain through space-time what is happening, and that will be part of the story.
So I'm going to apologize to everybody. I think we have to cut off our discussion, but I'm going to encourage people to go to the Slack channel and continue discussing there. And I'm going to hand it over to Nathan because we have more speakers, or Pedro.
Yes,
or
thank
whoever.
you very much. It was wonderful. Thank you.
So we have, thanks very much. So we have actually another discussion today, and next week we have lots more. So, Cliff, do you want to try to share screen?
Yeah, Cliff already did, and it was working. Yeah, Kristan is restarting.
Okay,
so you have to make a Jan de Boer, Jan iPad co-host. It's just Jan, J-A-N.
Okay. on. Okay, so I think we can start. So Henry, do you want to introduce the first speaker?
Yeah, thanks. So after that very enlightening discussion, I hope, we're very happy to have Clifford Jensen, who is going to tell us about Fredholm determinants, I think. So if you're ready to share, Clifford, then please take it away.
Hello, everyone. Let's see. I tested it earlier. Hopefully it still works. And here we go. Is that visible?
Yeah.
Ah, excellent. Okay, and hopefully everyone can hear me.
If you can make it larger, it would be good.
No, I haven't started the you know, thing yet. 1 second. And that should now be full screen. Is that correct?
Perfect. Yep, perfect.
Okay, shall I start?
Yes.
Yeah, please.
Okay.
You have a little pop-up on your screen with the
Oh no, have I?
built effects.
Yes, shouldn't see those. Showing all the, that's odd. Okay, I apologize. Okay, so I am going to get rid of all of that and hopefully it should go. So the discussion, has that gone now? Thank you.
Yes.
The discussion that we had just now, I think, is a nice indication of what I wanted to start with. Perhaps it's a bit old-fashioned to say this, and perhaps boringly controversial in some ways, but I think that we're not going to fully resolve all of these issues to do with black holes and other aspects of quantum gravity to everyone's satisfaction if we're sticking too much to approaches that link too much to space-time geometry. And what I mean is, again, the somewhat old-fashioned view that we know that geometry is likely emergent in a full theory of quantum gravity. And in some sense, we've perhaps been lucky in that we've had a remarkable number of successful computations that seem to be along the right tracks by picking various geometrical objects we like in the semi-classical approach and sprinkling some quantum stuff on it, and great things have happened. But I suspect, and maybe many of you agree with me, that that's only a piece of the story. And it might be that as long as we continue making different choices about what those favorite things are to play with, we're not going to all agree. So what I try and do is keep an eye out for tractable models of emergent space-time geometry, because I think we should learn from them. And let me say it a bit stronger. I think we should scrutinize models of that kind for lessons about how to perhaps use a different language to address some of this. And so, of course, one of the things that's been of interest to me has been JT gravity, because I think it's a great model of that sort of thing. Now, JT gravity on some manifold M is extremely interesting. It arises in a number of different contexts. For example, 2D quantum gravity in its own right, with black holes and wormholes and all kinds of interesting things. And of course, it also has a connection to the low temperature quantum dynamics of higher dimensional black holes. There's a whole ton of references I should give here, and I apologize that I haven't. Let me refer you to earlier talks that have talked about JT gravity and 2D quantum gravity. And for the high dimensional connections, I could refer you, for example, to a really nice talk by Sandeep Trivedi, I think last year or the year before in this strings series. But apologies to people I've not explicitly referenced. So the point is, what happens beyond that? And it's one of the things that I really hope that we can address in some model. And the reason it's interesting in JT gravity is because it's a toy model, but it has all of these interesting things, including the connection to higher dimensions. So that's the motivation for me. Beyond working on some manifold M, there is some story which is non-geometrical. And it's a model, once you include non-perturbative physics, where you can actually see the space-time geometry hand over to a non-geometrical description. And that's the sort of thing I think ultimately we need. So what has happened over the last 18 months or so is that I've developed various techniques for deriving explicit non-perturbative physics in JT gravity, and indeed not in just some formal sense, but actually allowing you to calculate things. And so in case I don't get to it, here are some things that you can calculate. The corrections to the Schwartzian that we all know and love. There are non-perturbative undulations that I will talk about. I'll show you how to derive those. You can use that to compute the spectral form factor that Steve Shenker talked about, for example. You can compute that fully in a non-perturbative sense in a full theory of JT gravity using these methods. And as came out last week, and I'll tell you a little bit about it at the end, a puzzle that has been in the literature for the last year or so involving how to compute the quench free energy. I can calculate that now, and there's the answer. So let me show you some of the things you need to be able to do that. So the key thing, first of all, let's remind ourselves about JT gravity. I'll be very brief. Here we have the usual setup. In particular, for the kinds of things that I'm talking about, I'll need to emphasize the fact that the Einstein-Hilbert action in 2 dimensions is, of course, topological. This parameter S0, which is the extremal entropy, is always going to is in front of that, and so whenever I compute on some manifold M with Euler number chi given by the number of handles and boundaries, I'm going to get a factor like that. And so we'll keep track. Topological expansion then will be this, and non-perturbative precisely will mean when I no longer have this expansion, beyond that expansion. So what do I have? I have a partition function, for example, the case of b equals 1, and it has some topological expansion plus corrections. And we do the usual things, and refer you to the papers, in order to compute the disk level, the leading order partition function. It looks like this. And by Laplace transform, I can extract some density of states, which is the famous Schwartzian. And there's a sketch of it. So what we're going to do in a number of steps is correct that Schwartzian, not out here in perturbation theory at large E, but deeply in here. So the landmark result on which everything stands that I'm going to do is the remarkable result of Shard, Shenker, and Sanford that the path integral, the JT gravity path integral on some manifold with factors like that then is connected to everything you compute here, you can compute here in a very nice framework, a double-scaled large N random Hermitian matrix model. There's an expansion parameter there, as Tuff taught us. The 1 over n expansion parameter is also a topological expansion, and it looks like that. So the matrix model looks something like this. There's some partition function. I've put a hat over it just to distinguish it from the previous partition function, which it is not. And there's some potential, which I'll call V. And if we're field theorists, we look at this as something we can do Feynman expansions of, and we write Feynman graphs. We draw their duals, and then we realize that the different vertices correspond to tessellating with different shapes. Interestingly, the double scaling limit means I take large N and I tune the couplings in that potential to some critical values such that large surfaces dominate. You end up in a limit where you have smooth universal physics of the gravity theory emerging, depending upon what the gravity theory is, which implicitly depends upon the potential that you chose. The triple S connection then is that there is some connection, not some connection, there's an equal sign between the partition function of JT gravity, for example, and an insertion of a thing that in the old language you might call the loop operator in the double scaling limit. Some important comments are that this is inherently perturbative using some beautiful checks that they did. based on topological recursion properties of the various objects that show up in doing the path integral as characterized by Mirzakhani, and then cast in loop equation language by Engelhardt and Orentin. It's important to realize that V is not explicitly known. It's enough because of those recursion relations to specify the leading spectral density, and then recursion tells you how the rest of it works out. And it is highly non-trivial and quite remarkable that it matches to all orders in the matrix model. I should also point out that there's a generalization and the classification to other models in the JT class by Stanford and Witten, which followed soon after. There are partial non-perturbative insights in these papers, but I think it's fair to say that the story was only touching on the beginning of the story. So I want to tell you one way of ending the story. So first, I think it's useful to go back to random matrix models and remind ourselves how they work. I'll use the simplest model I can think of, the Gaussian unitary ensemble. And this is simple enough that you can find all the equipment you need at home. So have a go. And you can simply take Hermitian matrices with some probability, some Gaussian probability. That's what that simplest model I wrote before with no higher order terms in the potential really means, as taught to us by Dyson. Not Dyson, by Wigner, or perhaps Wishart. We compute eigenvalues and then just histogram them, and this is what you get. So as you know, eventually what happens is that things settle down and there's a universal shape that seems to appear. I've done some scalings in order to write that shape, and it looks like this, and it's the famous Wigner semicircle law. Now, what the double scaling limit tells you to do is actually focus on an endpoint and zoom in. So I write lambda equals -2, say this endpoint, plus a little bit. And there's a precise scaling you need to do in order to magnify that region with n. And if you work it out, the power of n is 2/3, and on the bottom line. And there's a parameter delta that I'll use as well to scale everything nicely. So you go ahead and you do that, you plug that into here, and you look at what happens to this, and you get this nice rearrangement. What I've done is I've gathered things together into this nice piece here, which I'm calling row 0 without a hat on it of E. And what I've done is I've defined a parameter h bar, which is sort of renormalized 1/n. As n goes to infinity, delta goes to 0 in the limit. And that's typically what happens in double scaling limits more generally with these models. Well, let's actually go back and just roll the dice again and have a look. And what actually happens if you zoom in that same way, you'll get this. Now, if I did a bit more, some more samples, I would fill that in, but you can see what's happening. There's a pattern developing, and that pattern developing is the actual famous wiggles that you get on top of the root E behavior. Now, that magnification captures everything I want to talk about in some ways. It's a toy model, but it's very good. It can be written in terms of Airy functions, and there's an expansion in what I'm calling h bar, which is 1/n, but there's also non-perturbative pieces. Now, why is it called the Airy model? That encourages me to tell you a little bit more about some of the useful technology, and that is orthogonal polynomials. What you can typically do is rewrite these matrix computations in terms of polynomials that are orthogonal with respect to the measure. Now I'm working in the eigenvalue basis. And there's some relation that looks like this. And it's sometimes convenient to rescale things by this factor here so that it's orthonormal, and then write the integral as some sort of bracket notation like that. There's a recursion relation between the orthogonal polynomials. And for example, in the Hermitian case that we were just talking about, these are actually Hermite polynomials. And the recursion coefficient is just n, the index. Everything can be reduced to computing the Rn. And if I know these, I know the full answer. More generally, when I have V, you get a much more, you get much more complicated recursion coefficients. And so you end up with all the content still being in the recursion coefficients encoding V. Now at large N, I can write the index over big N as some continuous coordinate like that. The polynomials become functions. The recursion relations become functions. And in the double scaling limit, then these scaling pieces I talked about in the example before survive. So I get E surviving from lambda. I get some little x surviving some big X, which is valued in the reals. 1 over n becomes that renormalized quantity, h bar. These p's then become these functions psi, and r becomes a u. If you actually dig a little bit deeper, you can ask what happens to the operator lambda when I stick it into the bracket formalism. And you can see what happens. It's basically this recursion relation here. When you do the scaled version of it, you see that lambda as an operator becomes a Hamiltonian with potential given by the recursion coefficients. This is now a quantum mechanical theory. The wave functions are the orthogonal polynomials, or the orthogonal polynomials become the wave functions, and the spectral density becomes, and I've done no approximation here, it turns out to be the integral of the square of the wave function over part of this X region. So that's the story. The Hermite polynomials themselves become Airy functions and build the wave functions for us. And there's a beautiful story of how that all works, and you can do the integral and get what I wrote before. So that's what this looks like. Now, this is just a toy model. The Airy model is not a model of surfaces. It is very interesting in its own right, but for here, it's just an illustration of the power of this approach, because I have all the tools I need now to tell you how this generalizes. The Airy model, it shows us things through the fact that what I'm doing is I'm using this formalism. I have this little function u, this function little u, and knowing this potential in general is a great way of diagnosing problems and also figuring out how to define non-perturbative physics. And so my job over the last 18 months was to convert a lot of the known information, the known approaches into this language where you can get access to some of these crucial answers to some of these crucial questions. For example, Airy has a precursor problem, a precursor of problems for triple S. There's a leaking non-perturbatively of energies into to negative values, and they are avatars of a full non-perturbative instability for the full triple S theory. You can see where that comes from in this language. It's simply the fact that when I do this integral, I pick up the tails of some of the Airy functions that are at negative energy. That tells you also how to fix the problem. You simply don't have those tails. What you do is you look instead for potentials that are the same at high energy, so they'll have perturbatively the same physics, but at low energy, they cap off in this way. Now, I didn't just make this up. It turns out that there are matrix models that do that for you. And so you can actually write down a model of complex matrices with some potential that's built out of M dagger. So it's really, you can think of it as a model of Hermitian matrices that are intrinsically positive from the outset. It turns out that almost precisely 30 years ago, I worked on some of this stuff and helped develop the kinds of equations that you need as part of my thesis work. And so you can sort of go back and look at some of that work and see how to convert it into the modern language. And one of the things you see is that the resulting row, if you look in this paper, is very similar to the Airy function, but then it ends very nicely at equals 0. So this isn't done by hand. There are matrix models that perturbatively are identical to the Hermitian matrix model that will give you better non-perturbative physics. Now, the challenge, of course, is to extend this to full JT gravity, and this is what I did and variants thereof, and this is what I did in a series of papers. What you have to do is you have to identify the Hamiltonian. So you have to find an equation for U, and the equation I briefly showed you on the previous slide is a form that you will always get for those kinds of models, but the content is different. I should have said a little bit more about it, but time is short. So there's some nonlinear equation you can write down for U, and you can solve it. It's tricky. It turns out that the equations are formally of infinite order, but you can truncate them. And if you truncate them to high enough order, I think 15th order will give you a good solution. You can solve that nonlinear differential equation with a bit of care. You'll get a U. You can then solve the spectral problem. Again, it's tricky, but you can do it. And then you can compute this. And here are some results. So there is a sort of potential you get for JT gravity. And this is the result. You get wiggles as promised. So this is by now fairly robust package of things to do. It gives you full non-perturbative definitions of JT gravity and various variants. These, I should remind you, are explicit results, not merely formal. So you can compute useful things with it. For example, the spectral density, as I did in those initial papers. You can really learn a lot of what happens non-perturbatively to some of the questions. The point is that you cannot get this plateau region and the crossover into it in any of the perturbative approaches to JT gravity. You need non-perturbative physics. So you can do more. Refer you to the papers. And with collaborators, I also examined some other issues. There's some lovely work by Witten and also by Maxfield Churiachi talking about deformations of JT gravity and how those look like as matrix models. And again, you can ask what's going on non-perturbatively with those models. And with Felipe Rousseau, I wrote a paper on that. With Rousseau and Svesco, there's a rather nice and mysterious model of Stanford-Witten's, which is another JT gravity variant, which you can realize is a two-cut matrix model, and we did it in that paper. I should also mention that there's a lot of very exciting work that's adjacent to this, corresponding to minimal strings and Louisville, etc., that I think Thomas talked a little bit about, and that's relevant in terms of understanding how to build these models in terms of minimal string models, but I didn't have time to talk about that today. There are also other non-perturbative definitions discussed in SSS and also in Gao et al. Recently that are alternatives, and it would be very interesting to understand them, but right now they're very difficult to work with. You can't really calculate much with them, no disrespect intended, they themselves agree. So it'd be nice to have those developed and to put them alongside some of these and to calculate some of these things. Now, that's not all I wanted to tell you about. I don't know how much time I have left, but
Clifford, you have about 5 minutes left.
Really? Okay. Okay, so here we go. I'm going to go at breakneck speed and tell you, let's go back to the sampling that we were doing before. Okay. And now I'm going to say, instead, keep track of the order of the eigenvalues. You've got a matrix, keep track of the first, second, third, maybe color code them and run it again. And this is what you get. So what you see is now I've color coded things. I have different contributions, which are in some ways now telling you in some resolved way what those underlying wiggles are. Those undulations in rho, those non-perturbative undulations, this is the Airy model, are in some ways the individual, well, not in some ways, they are precisely the underlying energy states, individual statistics. You have individual peaks. What happens very crucially is that they get sharper and more dense as you go to larger energy. And in some sense, they form a continuum. And that's the regime in which we do gravitational computations using manifolds, etc. As we go to this regime, that eventually breaks down. But what takes over are these states and their statistics. So the model doesn't care about what you call geometry. It just computes. And at the end of the day, we're up here doing things in terms of manifolds, etc. But down here, we have to use a different language. Now, this is just the Airy model. You might ask, well, can I really do this for JT gravity? And the answer is yes. Let me tell you what the tool is that you need. So I'm just going to jump. There's another thing I wanted to show you, but I'm going to jump. And the tool you need is the Fredholm determinant in order to do this. We already have the components, it turns out, and that's the wave functions. So what you need is to put them together in a nice way. And it turns out you assemble them into what would be called, in the Airy case, the Airy kernel. You do this integral, and you can see it's actually a matrix for which the diagonal part is the spectral density that we talked about before. But there's a more general object, and all of that off-diagonal stuff has information in it, and we can use it. So in the random matrix model literature, you'll find kernels of all different kinds. One of the nice things is that JT and all its variants, as defined in the way that I'm using the language, defines a whole bunch of interesting new kernels. So that ought to be interesting. I was going to tell you why it's called a kernel and Fredholm, but there's no time. The key point is that the determinant of this thing is a very natural object in random matrix model literature, and I think it's a very natural object to use in gravity. And what you actually do is you can find out, for example, what's the probability of not finding, say, the first level in some interval, and you compute this object, unfortunately called E, and it's the determinant given as follows. That's a cumulative probability, so you need to take the derivative to get the probability distribution, and it looks like this. So far out here, I haven't found one yet. I start finding them, and by the time I get far out, I've probably found all of them. So that's the way to think about the cumulative distribution. Now the point is that you can get other levels by recursively using this in ways I don't have time to go into. It's a challenging problem to compute the determinants of these infinite dimensional operators, but it turns out that there are some techniques due to Bornemann that are very helpful, and I can do it for JT gravity, and this is the answer. So this is our third refinement, our second refinement of the Schwarzian. There's the Schwarzian, the dotted line. There's the wiggled lines that I found last year in a variety of models modifying, finding non-perturbative contributions. And now you can resolve what deserve to be called the individual microstates. And the really very important thing here is that this is not just a two-dimensional model. This also tells us about higher dimensional black holes. And so in some sense, in some limit, we're also getting access to a description of the higher dimensional black hole microstates. Let me remind you then, the geometrical description is good in this direction. These essentially become spikes and form a continuum, and gravity and geometry takes over. And in this direction, you need something else. And the matrix model can do all of it, and it's completely tractable. So that's why this is interesting. If I have all of the microstates and all of their statistics, I can actually compute everything. That is the complete matrix model. And I do have all of that. So I can compute, for example, something that's hard to do from other perspectives. I can compute the quench-free energy. The quench-free energy is very important because I need to follow the thermodynamics all the way down to low temperature. There's some really
just let
nice...
you know you're running into your question period.
Okay, I'm going to take one more minute. Thank you. There's some really nice discussions, for example, by Engelhardt et al. About using replica wormholes to compute it. One of the things that I emphasized in an earlier paper is that you really need to get access to the non-perturbative physics to finish the story, perhaps the matrix model. There have been various papers that have found some partial results, but now we can just do it with all of these microstates that we have, and that's the answer. So in view of the time, I think I'm going to stop here, make some comments. There was another movie to show you how that all works, but there isn't time. There's some comments about how this realizes some of the things that were anticipated by some authors at the very low energy level, but this is the full thing. No toy model, no approximations. This is the answer. I should also mention that sadly, there's no sign, as I guessed last year, of replica symmetry breaking. It seems that the matrix model isn't interesting enough. So I'm going to jump to the end, and thank you.
That's all. Thank Clifford. If there are any questions, then please raise hands. Julian.
Yeah, hi, thanks. First of all, Clifford, thanks. It was a really clear talk. I enjoyed it a great deal. So these new matrix models, I just wanted to know, maybe you can say a little bit more about their properties. So in particular, since they are not Hermitian matrix models, I mean, how do they arise, for example, as a boundary theory or as a limit of some boundary theory?
That's a great question. First of all, I should say, in some sense, they are Hermitian matrix models. They are, you know, if you just were doing perturbation theory, which is what we've been doing, and you started out and you were saying, oh, I must use some Hermitian matrix model, you could well have just started with these. Traditionally, we start with the less constrained type, but the fact that these are Hermitian matrix models with which are positive is it really comes in only when you get to the non-perturbative sector. So, you know, if you ran history differently, perhaps you would have started with these. Ironically, actually, history did run differently. Wishart matrices, in fact, are what these are in some ways. The Wishart matrix models, which predate what Wigner did in the 50s by some 20 years or so.
Okay, thank you.
Yeah, so I think we're, to give Kristan his proper time, we're probably should move any other questions to the discussion session, which I think immediately follows Kristan's talk. So Igor and Sandeep, write your questions down for Clifford. But let's thank Clifford again for his
they should go first then,
wonderful
and
talk.
I'll be around for the discussion. Thanks, everyone.
So Kristan, if you're there and ready to go, then please share your screen.
Let's see if it works this time. Oh, okay. Still not working. Okay, so I have to do a backup option. It's nice to see all of you, even through the black boxes on the computer. Let's see. See, actually, sorry. That did not work.
Sorry, that worked. We were seeing two screens, but that worked.
Okay.
I think you just have to mirror displays. If you go to displays, they are probably not mirrored. So if you mirror displays and then try again, I think it should work fine.
Let's see. I've been teaching a course for the last 8 weeks and did not have any problems the entire time with sharing Zoom. Let's see. Okay, let's try this one more time. My apologies again. Okay. Can you see that?
Yes, perfect.
Okay, wonderful.
I think take it away, Kristan. The virtual floor is yours.
All right. Well, many thanks to the organizers for putting this together in these trying times, and also for giving me the opportunity to speak today. I'll be discussing results in a series of papers co-authored with Jordan Cutler, an excellent postdoc at Harvard, over the course of the pandemic. And we have a lot of ground to cover, so let's get to it. So the past few years have seen a suite of recent developments in soluble models of 2D gravity, and space-time wormholes have been one of the key figures in those works. You know, for instance, wormholes yield non-perturbative effects in Jaquet-Titaboyne gravity, informing us that the dual of JT gravity is an ensemble of Hamiltonians rather than a single quantum mechanics. And further, they describe the statistics of that ensemble. And that's only scratching the surface. They've played a key role in many more developments, at least within the friendly confines of 2 space-time dimensions. Of course, one of the reasons why many of us started studying JT gravity and its cousins was to learn lessons that would ultimately apply to higher dimensional gravity. With that in mind, the main goal for today is to develop machinery to study Euclidean wormholes in more than 2 dimensions, including in lamppost examples of ADS CFT, like 10D supergravity on ADS 5 times S5. Now, we are well used to the story of black hole thermodynamics in Euclidean gravity. Goes back to the 70s. The Euclidean black hole amplitude with a boundary of the form of a thermal circle times some space, say a sphere, it encodes an approximation to the density of states of the black hole. Classical gravity doesn't describe the precise details of the microstate spectrum, of course, whose level spacings one expects to be non-perturbatively small in a UV complete theory of quantum gravity of order e to the -1/g Newton, but it's good enough to describe the coarse-grained approximation. What we do is to find Euclidean wormholes which interpolate between 2 asymptotic regions, each with the same sort of boundary, thermal circle times some space. Besides finding these wormholes, our main result is to present evidence that these wormholes encode an important feature of black hole microstates, a coarse-grained approximation to the 2-point level statistics. In particular, we find evidence for long-range repulsion in the microstate spectrum. In fact, it's very reasonable to expect such repulsion. If you put a large N holographic CFT on a sphere, then you effectively have some complicated many-body Hamiltonian with a large number of degrees of freedom. And generic many-body Hamiltonians have a chaotic spectrum of energy eigenstates. So it seems reasonable to say that this applies for the unprotected part of the spectrum of n equals 4 on a sphere. Now, by chaotic, I mean that there's short-range repulsion between neighboring energy levels, which builds up to long-range repulsion. Both the short and the long-range repulsion are nicely diagnosed with something called spectral form factor that Steve Shenker nicely summarized in his talk a few days ago, appeared in Clifford's just now, and so on. It's, if I was doing this on the iPad, I could actually highlight it on the screen where it is. It's this thing, the Z of beta plus IT, beta minus IT. It's this 2-partition function object. There's some real-time evolution T in there, along with an inverse temperature beta to tame contributions from high energy states. The spectral form factor has some features which are robust for many different quantum systems. At early times, it dips on this plot here between times of order 1 and 10. But then at late times, it oscillates wildly. Now, if you perform either a rolling time average or a small ensemble average, then that's sufficient to smooth out the wiggles, and you end up with a smooth curve like the black one here. The long-range repulsion corresponds to this regime where this, again, I wish I could draw on here, where the black curve is increasing. It looks linear and actually is linear, even though this is a log-log plot. So that growth is linear in time t. And then it levels off to a plateau at late times, which follows from underlying discreteness of the spectrum. Now, our wormholes that we consider being a 2-boundary quantity are computing a contribution to ZZ. And so if we continue the inverse temperatures on the 2 boundaries, beta 1, beta 2, in this way, beta plus IT, beta minus IT, then these wormholes are contributing some non-perturbatively suppressed contribution to spectral form factor. However, at late enough times, that contribution is actually larger than the leading disconnected contribution that you get from summing over saddles. We can then look for a ramp coming from these wormholes. Now, the central problem we run into is that these wormhole amplitudes are they're non-perturbative effects in gravity, akin to instanton corrections. But unlike instantons and 40 Yang-Mills, these amplitudes lack a saddle point approximation. And in fact, one can prove this statement thanks to a theorem of Whitman and Yau. In the absence of saddle points, we can choose to either give up on the problem or to persist. We're stubborn, so we persist. And our approach is, in a nutshell, to take Einstein gravity seriously as an effective field theory and to imitate what we would have done were this a problem in quantum field theory, at least as long as we can remain in a regime where an effective field theory description is valid. In particular, we adapt methods from field theory that have been developed to tackle analogous problems. Instant-on corrections when there's, strictly speaking, no instant-on solution to the field equations. All right, here's the plan for the rest of the talk. That was the introduction. Next, I'm going to discuss a particular wormhole amplitude in pure 3D gravity where life is sufficiently simple that we can compute at loop level. From there, I'll discuss wormholes in Einstein gravity and ultimately in 10D supergravity. We'll continue with pure 3D gravity. There's been an expectation dating back to Maloney and Witten that 3D gravity with negative cosmological constant is inconsistent as a theory of quantum gravity. This has been revisited recently, and there's now an open conjecture that 3D gravity is consistent after all, a dual to an ensemble, where the non-unitarity identified by Maloney and Witten is healed by a sum over all three manifolds. Given that we don't have control over a single chaotic C greater than 1 CFT, it isn't clear if a dual ensemble even exists, but nevertheless, we can proceed by trying to make sense of the sum over three manifolds, i.e. to do gravitational computations as best we can. Now, if one takes this conjecture seriously, then you would arrive at the following dictionary between bulk and boundary. If you fix a boundary, say torus of complex structure tau, and then fill it in all possible ways, well, what is that? Well, that's the average partition function in the dual. You fix two boundaries and fill them in all possible ways, and that's the average 2-point function, and so on. With this in mind, we focused on a particular two-boundary amplitude, which would contribute to the variance of partition function. And the simplest topologies for such a wormhole that we can consider, well, they're of the form Riemann surface times interval, where the interval is the radial direction. Since the torus partition function has the state counting interpretation, we focus on the case where this Riemann surface is a torus, so that we can use the wormhole to diagnose level statistics. So we would like to compute the torus times interval amplitude of pure 3D gravity. This amplitude has no saddle point approximation, and so requires some care. Here's the brief version. We pass to a first order formulation of 3D gravity, where one integrates over Dreibein and spin connection instead of over metric. Then we take advantage of the fact that torus times interval is topologically the same thing as annulus times circle, which we can think of as a Euclidean time. And then in first order, the time components of fields, the Dreibein and spin connection, they appear linearly in the bosonic part of the gravity action before worrying about gauge fixing. And so they act as Lagrange multipliers, at least to one loop order anyway. So integrating them out enforces constraints, which in 3D we can solve. We can completely solve them. And we can then perform functional integral over the constrained space. And the result is this formula in the blue box. Now, if you stare at it a bit, you'll notice that there's a single Maloney-Witten-like modular sum. But even so, this expression is in fact invariant under independent modular transformations acting on tau1 and tau2, the two boundary complex structures. So and this is great, from the 3D point of view, this had to be the case. And the fact that it is for this amplitude poses a very strong consistency check on our result. In fact, using some physical inputs from 3D gravity, we designed in a paper that followed up shortly after this one, an unconventional modular bootstrap, which was able to yield precisely this result for this amplitude up to normalization. That is, this amplitude is almost completely determined really by symmetry and consistency conditions. Okay, well, what was the point of this? Well, we wanted to study spectral statistics that's encoded in this result. Because in a many-body quantum system, different energy eigenstates, which are related by symmetry, well, related by symmetry, they don't repel, we decompose this result into contributions coming from different superselection sectors, which in this setting means primaries at fixed spin. Doing this yields a rather intricate result, which at low temperature assumes a very simple form that I presented here. There's corrections which come from this SL2Z sum. This is the order 1 minus beta on the slide, and they're somewhat complicated, but we have some handle on them. The dots indicate contributions from other tree manifolds, which we know much less about. Now, the leading behavior is something, this square root beta 1, beta 2, blah, blah, blah. Well, this is something that will look very familiar to those of you who are familiar with random matrix theory and the guts of JT gravity. It's precisely what one would find in a random matrix theory ansatz imposing Virasoro symmetry. And when I say precisely, I really mean it, like including the factors of 2 pi. This result, then, if you stick in beta 1 as beta plus IT, beta 2 is beta minus IT, well, it gives you Lorentzian spectral form factor. And, well, when you do that, you find a ramp. The square root beta 1, beta 2 is approximately t, and all the other contributions are subleading at large Lorentzian time. So you get something that grows linearly in t, and, well, that's a ramp. From this, we infer long-range repulsion in the spectrum of BTZ microstates. So okay, putting this together, this is perhaps the best evidence yet for an ensemble dual then to pure 3D gravity. This is kind of a smoking gun, which, if it exists, would evidently be some generalization of random matrix theory. Okay, let's move on to discuss wormholes in Einstein gravity. As I mentioned earlier, the vanilla sort of wormholes that we're interested in with S1 times a sphere boundary, well, they're not solutions to Einstein's equations. So what do? Fortunately, there's some history in quantum field theory of computing instanton amplitudes where there's no saddle to expand around. And most work in this vein falls under the moniker of method of constrained instantons. And a standard example is 40 Yang mills in a Higgs space. In that setting, there's no finite energy instanton solutions to the field equations, finite action rather, but there's still instanton-like corrections to amplitudes. And so to study these non-perturbative corrections, there was an idea that was originally suggested by 't Hooft and then developed later by Affleck and Affleck-Dine-Seiberg, which is the following. Take a quantum field theory with some fields phi, for which you don't have a saddle point approximation, and then foliate the integration domain by constant values of some constraint functional, mathcal C. For an intelligently chosen constraint, even though the full integral doesn't admit a saddle point approximation, the integral along one of these slices will, and call that saddle a constrained instanton. You get one for each slice. And then the idea is to do the full functional integral in 2 steps. You sum up first the contributions, the fluctuations around a given constrained instanton, and then second, you sum up all the slices, all the constrained instantons. And stated this way, it's clear that as long as you do things correctly, this method is just a convenient ordering. Which variables do you integrate over first in the functional integral? In practice, one inserts a resolution of the identity into the path integral, where here lambda is the Lagrange multiplier, as lambdas often are, fixing you to the constraint slice, and zeta is the possible value of the constraint. And the idea then is to integrate over the quantum fields and the Lagrange multiplier first via some weak coupling expansion, assuming it exists. And then one first integrates over fluctuations around some given constrained instanton, and then you integrate over the family. And this produces an integral representation here on this slide. Now, different choices of constraint will lead to a different choice of integrand. But the point is that since all we've done is insert one, the full integral better be independent of the choice of constraint. This is akin to something we're familiar with in ordinary diagrammatics. Some given amplitude, some given scattering amplitude, can admit multiple integral representations. What's physical is not the integrand, but the full integral. We then adapted these techniques to Einstein gravity. To proceed, we need an intelligently chosen constraint. On shell, the solutions to the 2-boundary problem at hand are disconnected spacetimes with an even more infinite distance than usual between the 2 boundaries because they're disconnected. turns out that we can find wormhole instantons if we constrain the length between the two boundaries. Using this constraint, we found several examples of wormholes. One of particular interest for this talk is this line element here, a 5D wormhole, which has S1 times S3 boundaries. Here, beta 1, beta 2 are the sizes of the boundary circles. Rho is a radial coordinate, and there's actually a whole family of these wormholes labeled by a parameter that I'm calling B. These wormholes are bottleneck geometries. They look kind of like this picture here. And roughly speaking, B controls the size of the bottleneck. Imposing that this space is regular implies a bound on this parameter, which in this case happens to be B greater than or equal to 1. That's what you need for the geometry to be everywhere regular. Now, all the wormholes we found, including the one on the last slide, have some features that are worth mentioning. Perhaps the most important one is that if we take the limit where the inverse temperatures, beta 1, beta 2, are equal and opposite, then these wormholes, what they become are Euclidean black holes, where the black hole mass is a function of this parameter B. If we made beta 1, beta 2 equal, opposite, and pure imaginary, you end up with a Lorentzian geometry, the double cone of Shenker Stanford, actually, which is a time-like orbifold of the two-sided black hole. And so these wormholes that we're finding are they're analytic continuations of black holes. Another fact is that, when you have a boundary in ADS, there's a boundary stress tensor. And if you compute the energies associated with these boundary stress tensors, they're actually the same. And they're roughly, b to the d divided by g Newton. You can exchange b for energy. And the renormalized action of the wormhole is actually very simple in terms of this energy. It's just the sum of the inverse temperatures, beta 1 plus beta 2, times this energy. Putting these facts together with our discussion of constrained instantons, you get an integral representation of the wormhole amplitude. You originally integrate over all possible values of the constraint. That can be traded for B, and then for an energy, which I'm calling E prime. It's a dummy variable. And the integrand of this integral is just the loop expansion around the wormhole of fixed energy. Now, the classical action I mentioned on the last slide leads to this Boltzmann factor, this e to the minus beta 1 plus beta 2 e prime. And that, looking at that, it tells us something very important. It's that this wormhole amplitude is dominated by wormholes with the smallest possible energies. And in gravity, what that corresponds to is the limit where the bottleneck is pinching off. Curvatures blow up, and effective field theory breaks down. This tells us then that, alas, the ADS wormhole amplitudes are UV sensitive. They cannot be reliably computed in effective field theory. You don't give up, though. We'd like to, even so, reliably extract physics away from this pinching limit, i.e. to somehow be able to access the integrand in a meaningful way and study wormholes of fixed macroscopic energy. Now, the amplitude so far is a canonical ensemble quantity where we fix boundary temperatures. And so you might wonder, well, what if we somehow are able to fix energies instead? Is that some way of blowing up and staying away from this pinching limit? And it turns out the answer is yes. You can fix the energies if you do that up to some resolution scale, delta, then that allows you to select a particular wormhole. It becomes a non-standard saddle, where one integrates not only over bulk fields, but also you integrate over boundary temperatures with some weight. That's what you need to go from canonical to microcanonical. And if the boundary energies are equal, then this non-standard saddle is precisely the double cone of Shenker Stanford. You track with this transformation.
Sorry, Kristan, this is your 5-minute warning.
Believe it or not, that's great. Okay, so this transformation from canonical to microcanonical, if you follow what it does to two-point function of trace e to the minus beta h, it turns it into this expression, the big one with the angle brackets, this sort of microcanonical version of spectral form factor. And how to say, if you look at the contribution from the wormhole then, you get to this, the result is linear in time t, owing to some twist zero mode of the wormhole. This was something that was noted already in Shenker Stanford. And the one loop factor around the double cone that we do not presently know. On bulk effective field theory grounds, though, one expects that to not scale with t, in which case you would get an answer that goes linear in t from gravity. Looks like a smooth ramp. In fact, it's very similar in functional form to the genus zero approximation of the same quantity in double scale random matrix theory, which I've also put just below it for comparison. We regard this as an evidence for a ramp in gravity and so long range repulsion. I should mention, well, okay, there's a second more brute force way of fixing the energy that I'm going to adhere to my time limit and I can't talk about. Having constructed wormholes in Einstein gravity with negative cosmological constant, we now have the techniques to uplift them to 10D supergravity. So let's do so. Fortunately, it's very easy to do this, at least for Freund-Rubin compactifications of string and M theory. For instance, the 5D wormhole with S1 times S3 boundary that I mentioned above, it can be uplifted to a 10D wormhole with a form just a direct product, 5D wormhole plus 5 sphere of constant size in type 2D supergravity with constant axiodilaton, no 3-form flux, and then a 5-form flux that's just fixed by Gauss's law. Once you have these wormholes, you can, in 10 dimensions, you can begin to investigate the question of their stability, both against fluctuations of supergravity modes, as well as against non-perturbative nucleation channels. In our April paper, we undertook a partial analysis of perturbative stability, focusing on the lightest sectors, the most dangerous instability channels. And unfortunately, it's more involved than what I can give justice to here. There's a certain, yeah. So let me skip ahead. And what I can talk about in the amount of time given is potential brain nucleation instabilities. The main one to worry about here is, since there's a 5-form flux background, is the prospect that D3 anti-D3 brane pairs, which don't change the flux at infinity, those can nucleate in the wormhole. And indeed, in the probe limit, we find solutions for 3 branes which wrap S1 times S3 and sit at constant radial coordinate and angle on the S5. And within the probe limit, we find that for generic values of boundary temperatures and bottleneck size B, that the action of this 3 brane pair, the solution to the brane equations of motion, is negative, which indicates an instability. The wormhole with the brane pair on top of it has a lower action than the wormhole without. The physics of that is screening. It's likely to have the brane pair in there, and that decreases the amount of flux in between the branes by 1 unit, which in turn decreases the size of the wormhole in between. However, it turns out that as we decrease the size parameter B, there's a critical value such that smaller wormholes become stable against this nucleation. And this critical value is importantly macroscopic. There's smallish, but still ADS scale wormholes, which are completely stable against brane nucleation. Turns out that there's another way to lift this nucleation instability, namely to take the continuation of the boundary terms required to get spectral form factor, so beta plus IT, beta minus IT. And if we track what happens to the action of the brane pair under this continuation, we find that this instability is lifted by a finite amount of time evolution. It's an amount that's at most of order B. So we conclude that the double get in the limit where this T is much, much larger than beta is stable against brane nucleation. Okay, that's wormholes, what they mean. Here's a slide about factorization. I unfortunately missed the discussion earlier today, small kids and such. So I don't know what people said. The wormhole amplitudes in this talk appear to violate factorization of the 2 boundary amplitude into a product of 1 boundary amplitudes. And at some level, we've been trying, what we're trying to do is to sharpen the factorization paradox in ADS 5 times S5 as best we can. In pure 3D gravity, it was perfectly fine to violate factorization. In fact, it tells us something useful, giving evidence for an ensemble interpretation. But in ADS 5 times S5, which we expect is dual to a single instance of n equals 4, the matter is less clear. And there's many questions.
Kristan, you're now into your question time. So
okay.
Up when you have a chance.
30 seconds. Okay. One question we might ask is whether or not there's a principle in string theory that just excludes the wormholes discussed from the start. I don't know how to begin answering that question. But if there is, I would say that would be a novel feature in quantum gravity. We're used to the statement that there's low energy effective descriptions, which can't be UV completed into string theory, that there's a swampland. But an exclusion principle like this, if it existed, would forbid us from summing over configurations within a low energy limit of string theory. There's also a very interesting suggestive recent paper of Shenker, Stanford, Yao, which Steve mentioned in his talk earlier this week. They're able to pose and solve a version of factorization paradox in 0 plus 0 dimensions using some collective field description of SYK fermions. Does that teach us about how we should think about, say, n equals 4 in strong coupling? I think it's not clear yet. The only known collective field description of n equals 4 is string theory on ADS 5 times S5, which right now doesn't give us enough non-perturbative fine-grained control to analyze these problems. And I guess I can mention that the techniques, this will be my very last comment before questions, that the techniques in this talk allow us to construct wormholes, not just in ADS asymptotics, but in asymptotically flat geometries, like the full D3 brane geometry. And without a dual CFD interpretation, in that case, I'm unaware of some theoretical prior for factorization. And so, there's a logical possibility, as far as I understand it, that maybe somehow, some way, factorization is sealed in ADS, but perhaps not in flat space string theory. I don't know. It's an open topic for future investigation. And with that, I'll stop talking. Thank you so much.
Thanks very much, Kristan. Wonderful talk. And to Clifford as well. I suspect the given time, our organizers might want to move straight onto the discussion, but hopefully that will be a good chance for those with questions to ask them, and if not, in the Slack as well. So I don't know if Pedro, you'd like to take over at this point, or if we've got time for a question or two now.
We can have one question, and then let's move to discussion. Let's move at 25 to discussion.
Okay. I think the Hiroshi was first.
So actually, you might have already mentioned it, and I apologize if you missed it. But given the issues with the fact that there are no saddles and there are UV sensitivities, to be certain that these wormholes contribute, it would be nice to know some explicit example where you are constrained wormhole, how they compare with boundary computations, which I think I missed. Could you elaborate on this point?
Sure. So, how to say, yeah, it was fast. So indeed, there's no saddle point, conventional saddle point of Einstein's equations that yields these wormholes. And so there's a question, how sharp is this factorization paradox? How much tension is there? And this was the point of these slides where we tried to fix the energy. So if we fix the energy, then we can get macroscopic wormholes. We're dealing with an unconventional.
Excuse me for interrupting, but I'm not asking about the bulk calculation. I'm asking, are there any boundary calculation for which you can actually identify the result of your calculation?
No. I mean, this is part of the problem. We don't, I mean, if we talk about n equals 4 at strong coupling, then I don't know of any way as of yet to compute the spectral form factors, say, in this regime. The only way that that I know of at present is through gravity, where there are these tensions with factorization.
Okay, yeah, that was my question. Thank you.
Okay, my apologies. Thank you.
So yeah, let's thank Kristan and Clifford again for those wonderful talks. I'm sure they'll serve as a beautiful warm-up for the lively discussion we're about to start. So with that, I'll hand it over to Steve and Jan. Yes.
Yeah, let me just say a few words. So I don't know if, yeah, I see Nathan unmuted himself. So Nathan, do you have a few remarks to make?
I just wanted to make a comment about the poster session. So the poster session will be just after the discussion. So as soon as the discussion finishes, we'll open the breakout room. So for the people presenting posters, you don't need to be co-hosts. Just be ready 5 minutes before we open the poster session.
Yeah, so let's move to the last discussion of week 1. Let's learn if we should average or not average. I remind you, the last 30 minutes are informal and we are not going to be very strict on time. The first 20 minutes are totally up to Steve and Jan. And in particular, they decided, for example, in this session, to give the floor to Douglas Stanford, who luckily can join us now. And so I'll pass it over to Jan and Steve, who will prepare us for the discussion to follow.
I think we agree that I would start out and then Douglas will take over. Kind of Douglas and Steve kind of flipped, and then we'll have a discussion with everyone else.
Perfect.
So I'll just start. So what I thought I would do is just mention a long list of questions. Like some of them are high level, so they're not like small technical questions, but many will be more high level questions. I will also have no references whatsoever. You can always choose between trying to be complete or trying to be maximally incomplete. So I decided to be maximally incomplete, also because Steve already gave a nice overview talk. Also, sometimes if you annoy and irritate people, you stimulate more discussion. So there will not be any references whatsoever. We already heard several talks about the subject. So I'll just start off by listing many questions. Well, wormholes, obviously, as we have heard, they seem to spoil factorization. This is obviously an important issue. And one way out with this apparent lack of factorization could be that gravitational theories are dual to ensemble averages, which immediately raises the question, what happened to good old alias CFT? Luckily, we now know the answer because we just had a poll and 55% of string theorists say that gravity is not an ensemble. And I don't think there's any community in the world that's more democratic than string theorists, so this settles it once and for all. And we could stop right here. But nevertheless, I'll continue for a bit and ask some more questions. So I think one perspective I would like to make is that if we do these computations in low energy effective field theory, then we get some partial information about the high energy sector of the theory. We get low energy effective field theory in general knows about high energy degrees of freedom, but only in some coarse-grained or blurred way. And I don't think in ADS CFT, we know exactly how that high energy coarse graining / blurring works, because we're doing a low energy effective gravitational theory, and a low energy gravitational effective theory behaves quite differently from standard low energy effective field theory, where we integrate out high energy loops in all the massive fields, and we know quite well what's going on. So it may well be the case that as far as low energy effective field theory goes, there is very little distinction between having a proper ensemble average, which is sort of, say, written here as like, so that we average over, say, finite temperature density matrices. I see there's a lot of response to my little poll joke in the chat, but I will try to ignore that. So there might, from a low energy point of view, be actually very little difference between having some sort of ensemble averaging at high energies or having some sort of unknown coarse graining at high energies. So as far as low energy effective field theory goes, maybe it's very hard to distinguish an ensemble average where the averaging takes place at a very high energy so that it has very little impact on low energy effective field theory versus maybe some sort of coarse graining or state averaging. But we don't know. This is just a cartoon, this expression here. You should not take it too literally. It is just meant to indicate that if we do some unknown form of blurring or coarse graining at high energies, and it could be because we take narrow energy bands and we do some unitary average over that narrow energy band, it could be that if from a low energy point of view, these are very indistinguishable from each other. And maybe all that we're learning is not that the theory is an ensemble average, but maybe what we're learning is that there is a very interesting notion of coarse graining going on. And many aspects of wormholes and so on can actually be captured equally well by an ensemble average or by various suitable notions of coarse graining. For example, it's quite easy to invent versions of coarse graining or state averages or whatever. And again, I emphasize we don't know how that precisely works in ASCFT. It's very easy to come up with a situation where the expectation value of the product of two density matrices is not the product of two expectation values. So that the average of the square of anything is not equal to the square of the average. That is very easy to obtain. And if you're agnostic about the type of averaging that we are doing at high energies, then maybe ensemble averaging and coarse graining are actually indistinguishable at low energies. So this is my first question. Is there actually a simple low energy diagnostic that distinguishes proper ensemble averaging from a suitable notion of coarse graining? We don't know what that coarse graining is. Maybe we're learning what that is. But that would be my first question. Can we distinguish these two things? One way to distinguish them is to just UV complete the theory and add more and more UV ingredients. And then eventually one expects one will see a difference between an ensemble average and a single unitary theory. Because if you go all the way into the UV, you can obviously tell whether or not you have an ensemble average or a single theory. But maybe at low energies, it's very hard to distinguish these two possibilities. And maybe this is the lesson that we're learning. And actually, in both perspectives, wormholes compute statistical fluctuations or moments of relevant probability distributions. So with these wormholes, we will not see this individual red noise. This is a picture I stole from Steve's talk. Thank you, Steve, for that. This red noise here is not detectable by wormholes, but we can compute the average amplitude of this noise and higher order moments of this noise using suitable wormhole configurations. So in some sense, with all these wormholes and so on, we seem to be probing moments of probability distributions, which could either be ensemble average probability distributions, or it could be a probability distributions that are coming from a suitable notion of coarse graining. Then, of course, there's a question, where actually does the noise come from in an individual instance of the theory? This presumably requires individual microstates. So one could try to approach this, say, from a microscopic matrix model like Clifford was doing. But if those microstates are not present in your low energy effective field theory, then you will also not be able to capture the noise. You might be able to see it if you have a complete UV completion, because clearly in a complete UV completion, we should be able to see the noise, but maybe at low energies, all we see is some moments of it and not the individual noise. So the second question is, where does the noise come from? The third obvious question is, how is factorization restored? This is the other obvious question. Again, it might be that at low energies, one sees an apparent lack of factorization, and that how factorization is restored depends on the details of the UV completion. It's possible, maybe, that the wormhole that you think spoils factorization is destabilized and no longer present. Maybe we should forbid it by some stringy exclusion type principle, but that would be an entirely novel principle, as Kristan was suggesting. It's possible to, in the UV, we find all the relevant fluctuations that restore factorization. And it's also possible that we do not restore factorization, and that would be compatible with having an ensemble average interpretation. So these are all logical possibilities that can happen in the UV. We have heard several talks about JT gravity in discussants. If you treat these JT theories as UV complete gravitational theories and not just as a low energy effective field theory, then they are remarkably described by suitable matrix models. It's a beautiful exact duality. Now you could ask, what's a single SYK sample dual to, or a single matrix, right? If we wanted to zoom in on the difference between ensembles and single unitary theories, it would be nice, but whether one could actually construct a more accurate dual description of these single instances. And the question is, can we do that? Is that a good question? In 3 dimensions, we can also study all these wormholes, and two questions that come to mind in 3 dimensions are, the first question is like, what's the dual of pure D 3D gravity? So now we try to treat 3-dimensional gravity as a UV complete theory. So we don't add all kinds of additional Kaluza-Klein towers and so on. We just take it as a standalone theory, and then you can ask, what is the dual? And what do we even mean exactly by pure 3D gravity? Do we need to tweak it or modify it? And another question maybe is, are there nice natural ensembles of holographic 2D CFTs that one can average over? The most obvious families are things where you have lots of moduli and you average over moduli, but maybe there's a more natural thing or a more general thing that one can do. Then I have 3 questions in, I'm almost done, in dimensions above 3. First question is that we see that this double cone seems to give a reasonable explanation of the ramp, also in higher dimensions, up to all kinds of subtleties that Kristan mentioned. You can ask whether the very long time scales that one is probing with the ramp is part of low energy effective field theory to begin with. We also seem to see a general phenomenon that Euclidean wormhole solutions, when they exist, are always subleading. And maybe there's a general argument that this must always be the case. Or maybe we find a counterexample, and it would be great to know what the implications of a counterexample would be and what it would imply for a possible UV completion that one could have. And one can ask an obvious question, does it make sense to average n equals 4 super-Yang-mills over, say, the complex coupling constant, or do something else? Take a small wave packet for like the complex coupling tau and see if you do a small average what that does to the bulk theory. And then there's a few questions that connect to other discussion sessions, like to have like a meta discussion session. So the first question is, can we connect it to the swampland program? In other words, can we violate some of the swampland conjectures if we do averages rather than single theories? I think most of the swampland conjectures implicitly assume a single unitary UV completion to exist, and maybe we can relax some of those conditions if we assume the dual is an ensemble average. The second question is also how to test for unitarity in the dual of average theories. Can you distinguish whether you average over families of unitary theories versus taking, averaging over some unitary and some non-unitary theories? And how do you test for that? What would be the smoking gun computation? It's a great question whether there's actually a deep connection between all of this and the bootstrap program, because wormholes seem to yield statistical information about the high energy sector of the theory. The bootstrap does that as well in some sense, like some rules, give you some statistical information about the high energy sector. And it's a great question whether there's a more precise connection to be made and whether you can, in fact, say bootstrap averages of theories rather than individual theories. There's an interesting question whether we understand the unitarity of the black hole evaporation process somehow. You could say that the fact that SS dagger equals 1, that means that SS dagger is something that does not fluctuate. And maybe because it does not fluctuate, it has like no variance. Maybe that is why we should at least be able to verify that it's equal to the identity with some low energy computation. So maybe things that do not fluctuate are accessible to low energy effective field theory, and everything that fluctuates is not. But it's a great question whether there's a deep lesson to be learned here. I think it's also an interesting question. The ramp seems to be related to, say, this double cone and so on. So this long range level repulsion seems to be accessible, but the short range level repulsion, which is quantified by the plateau, you can ask whether there's a nice gravitational argument that's a universal feature as well. If we believe the old statement that any quantum chaotic system should ultimately be described by random matrix theory, then there should be some argument for universality of the plateau in holographic theories as well. And it would be great, to know what that universality argument would be. And maybe for that we need a gravitational dual description of the Goldstone mode model that Alex Altland and Julian Sonder wrote down. Most of these factorization things have to do with Euclidean wormholes. There's an interesting question whether there's something new to be learned from Lorentzian wormholes in all of this. I don't have anything more to say about it. And my final question is about the whole baby universe business. And I think an interesting question is whether we can reliably establish or rule out that the baby universe and the superselection picture is relevant in a full-fledged solution of string theory, like with matter fields and everything, or whether it's a feature that is applicable to low-energy topological examples and low-dimensional topological examples, but that at high, in a full-fledged theory, it actually is hard to make precise. Is there like a smoking gun computation that will either establish this or rule it out? I think that's a great question. And I've asked many questions, and I'll hand the floor over to Douglas.
Let's thank Jan while Douglas sets up the screen share.
Okay, yeah, thanks. And thanks a lot to the organizers and to Steve Shenker for covering for me earlier this week. So, okay. So here's one possible take on gravity and wormholes and ensembles. Fine-grained quantum data, by which I mean like energy levels, operator matrix elements, are very complicated with no simple description. But one can imagine a simple effective description where these quantities are drawn from random distributions. So mathematically, we replace the pseudo-randomness by the complexity of pseudo-randomness by the simplicity of actual randomness. This idea kind of goes back to Wigner and thinking about atomic nuclei. So maybe simple gravity, by simple gravity, I mean low-energy effective field theory of gravity coupled to matter fields, maybe that is such a theory, describing a possibly fake ensemble of boundary theories with different fine-grained quantum data. In some special cases, like in pure dilettante gravity, both the bulk simple gravity theory and the boundary ensemble are separately well-defined and dual to each other. But more it seems more likely that both the simple bulk theory and the putative boundary ensemble are probably incomplete. On the other hand, they seem to be fairly detailed, going beyond just random matrix universality and ETH statistics. And it's an interesting question to wonder how far they go. So this is a little awkward because the rest of my talk has significant overlap with what Kristan discussed. So I'm just going to skip it to give us more time for discussion. And I'll just go to the end where I have a couple of questions relating to wormholes and ensembles. So this is the most important question by far, which is what are we supposed to add to the simple gravity theory to get a specific boundary quantum system, n equals 4 super-Young mills or something like that? This, I think, is the most interesting question. But here I want to emphasize that there's another secondary interesting question, which is to wonder how detailed is this fictitious ensemble of theories that simple gravity seems to describe? What is it trying to describe? What is the input to this theory? What is the output, and how far does it go? Okay, so I'll actually just stop there and leave more time for discussion. Thanks.
Thank you very much. You are well within time. You could.
Well, the rest of my talk,
I would like to hear what Douglas had to say. Could you go over your slides, Douglas?
Okay. So let me just try to go through an example of this in the simple context of energy statistics. So in ADS-CFT, the thermal partition function of the boundary is represented by boundary condition, which is a circle of length beta. So here's the circle, and here's the quantity that computes. It's the integral over energies of a Boltzmann weighted density of states. So for a real quantum system, rho of V is a sum of delta functions. And in gravity, the Euclidean black hole geometry can fill in this boundary condition, and it gives the leading gravitational answer for the density of states. So we fill in the circle with this geometry, and the result is this computation here, where this capital G means evaluation in a simple gravity description. And here we're going to try to interpret it as meaning an average over an ensemble. So here I'm drawing two-dimensional bulk pictures, but it could be higher dimensional. So a question to ask is the ensemble defined by this capital G non-trivial? And a wormhole like this one here would tell us about the variance on the ensemble. So this connected correlator of these spectral densities. Okay, so this wormhole would formally be computing this quantity here. but there's actually no solution. And the reason is that the wormhole wants to get long and narrow. The boundary interpretation of the fact that there's no solution is that this function, this correlation of the densities, is not growing with energy. So in this integral here, there's no saddle point. So we shouldn't really have expected there to be a solution. And it's actually super important that there's no solution, because if there were a solution, analytic continuation to Lorentzian signature would give an eternal traversable wormhole with no interaction between the two sides, and that would violate boundary causality. However, there are several ways to tweak this setup so that there is a classical solution. Here's 5. You can couple the two sides. You can insert heavy operators on the two sides, but not couple them. You can put spatially varying sources on the boundary. You can put imaginary sources, or you can study this case where beta left plus beta right is equal to 0. And the boundary conditions in the last 4 of these cases remain factorized. So the wormhole, which now exists as a classical solution, seems to require an ensemble interpretation in each of these cases. So I'm just going to make a couple comments about this 5th case here. Okay, so we want to set beta left plus beta right to be 0, but we don't want either of them to have negative real part. So what we can do is we can make one positive imaginary and one negative imaginary. And then what we're computing is this integral, where I've replaced the Boltzmann factors by this weighting by these phases. So because the sum of these betas is 0, the pressure coming from the Boltzmann factors is absent. And that means that a classical solution, a classical wormhole solution, can exist. This is what's called the double cone. And it has a periodic direction in the bulk with a geodesic length that's proportional to t. That's not obvious, but it's true. Okay, so if t is small, then this periodic circle is short. And the answer is UV sensitive, because we can have bulk fields propagating around this short circle. They feel like they're very high temperature state. So we need a more complete theory for this region. On the other hand, for very large t, the matter fields are projected into the vacuum by this very, very long circle. And the calculation is controlled. Also separately, and this gets to a question Hiroshi was asking earlier, in this limit, random matrix universality predicts an answer for this quantity from the boundary perspective. And the wormhole reproduces this answer. Okay, but there's a third region, which I think is interesting for kind of intermediate values of t, where there are exponentially decaying corrections from matter loops that can wind around this circle. And this is a prediction that goes beyond RMT. So to summarize this example, this simple gravity theory is incomplete, and the associated ensemble is incomplete, but it reproduces random matrix theory in the limit of universality, but also goes beyond it, has corrections beyond it. Okay, so that's all I wanted to say on that, and now I'll really stop. Thanks.
Thank you very much. Let's thank, please, all the speakers of this introduction.
Douglas, can you leave up your questions?
Yes, I'll do that. I mean, my questions are much less detailed than Jan's questions, but here they are.
Yeah, so as usual, please raise your hand and wave if your question is related to the comment that is being made now. And of course, Steve and Jan, override me at any moment. You know much better who to call next. Otherwise, I'll just follow more or less chronologically, and also the people that I will also call on people that did not participate yet. And by the way, Jan's slides that have many questions should be uploaded to the website very, very soon, maybe in a few seconds, or maybe they are already there. So, yeah, as I said, let's start with people that did not have a chance to participate yet. So, Greg.
Yeah, I just wanted to make a small comment about one of Jan's questions. Another possibly interesting ensemble, he asked if there are other ensembles of CFTs one might want to look at. And one possibly interesting one is just products of symmetric products of K3s and T4s. End of comment.
You mean averaged in terms of averaging those over the moduli, or?
Yes, exactly. They have a natural finite measure, finite volume.
So, sorry, but a comment related to that.
is it clear that that integral is going to converge? Because in the Narayan story, it's important that you never, insert more partition functions than the dimension of the lattice that you're integrating over. And in the orbifold theory, because basically you have a 4-dimensional lattice, but you're going to have n copies, I think you run into problems, and that may not converge.
Well, I think even in the rain case, the experts are here, they can correct me. I thought even in the rain case, you had to deal with some infinities. I don't know. The only thing I thought about was averaging the elliptic genus. And since you have these different components, it was still interesting. That's why I asked the question. I think nobody's looked at this ensemble.
Hiroshi?
Yeah, so we have actually looked at the related ensemble, which is just one copy of K3 target. And we have some tentative conjecture that a straightforward generalization of this Narayan ensemble case works only when critical central charge is equal to central charge, which is not the case for these examples.
So you're saying that if we take products of symmetric products, you're going to have.
Well, you can take average, but it may not have straightforward bulk interpretation in terms of simple gravity, whatever that is.
You are muted, Greg. I'm not sure if you are replying.
I'm not replying. I've said what I have to say.
Okay. So then maybe let's move to Henry.
Thanks. Yeah, I just wanted to make a simple point that there's not really a dichotomy between the ensemble from what Douglas calls simple gravity and having a unique dual theory or whatever language you want to use. That actually there's the ensemble is not a property of the theory of gravity by itself. It's a property of the theory of gravity and the state of closed universes. So the state of closed universes gives you a parameter to dial from an ensemble to a single theory. And I think that we can probably gain a lot of ground by thinking about what happens when we dial that parameter, when we choose the state of closed universes to be close to an alpha state, which corresponds to a single member of the ensemble.
Yeah, I guess my question was, how would you imagine doing a relevant computation, say in ADS5 cross S5 to test this idea? What would be a precise question to ask?
To test what? Sorry, yeah.
This dial, what would it exactly mean to dial and to choose an alpha vacuum as opposed to following the user rules of ADT? What would be the key difference?
So I'm thinking about you dialing the alpha, well, dialing yourself to an alpha state is something you do in what Douglas called simple gravity. So simple gravity, if you take this seriously, is describing an ensemble dual, if you like that language. And so, for example, Hawking's calculation, it gives you a way of saying that Hawking's calculation is correct, but the replicable wormhole calculations of the page curve are also correct. And so it puts everything in a coherent footing. And in that theory of simple gravity, the way you would dial to an alpha state is, for example, by creating many black holes and making projective measurements on the Hawking radiation. And that's something you can describe explicitly in this simple theory of gravity. I'm not so much saying how you distinguish between simple gravity being an ensemble and being a unique theory. I'm saying if simple gravity sits in this ensemble paradigm and you believe that, nonetheless, you can dial yourself to a single relevance to the theory. And if you think you're true, say n equals 4 as a particular theory, you might hope that it looks very, very similar to a generic alpha state in the simple gravity theory that describes an ensemble. So for example, the statistics within the ensemble at fixed energy would, for exactly the reasons you said, that it doesn't really matter how you average, that should tell us something about the statistics of microstates in a specific theory. Because again, for all the reasons you described.
Right.
So if we want to learn about the statistics of fuzzballs, then we can do that by learning about the statistics of an ensemble in simple gravity. So that's the hope.
I see. Yeah, I think you're. Yeah, I think maybe we're all saying roughly the same thing with slightly different words at the end of the day. I am not exactly sure. Maybe Steve wants to chime in at this point.
Okay. I've had my say, so I've been trying to be quiet. But I guess Henry, I'd ask you. I mean, I think the question maybe is: do you think that there is such a thing as a gravitational path integral that will compute simple gravity on the nose, that will contain all the fuzzballs and everything else, like compute the ensemble average spectral form factor, the exact shape of that red curve in Super Yang-Mills? That's the question.
I think that's the right question. I don't have a good.
Sorry, maybe let me ask something, because maybe I'm a bit confused by this new language, simple gravity. I never heard it before. Sorry. So in N equals 4 Super Yang-Mills, simple gravity is the usual one I'm used to, or it's something different?
Well, what is the bulk in Super Yang-Mills? That's kind of the question that we're dancing around. I mean, we know some things about it, but I think underlying this, there's somebody that's not muted. I guess is it? I don't know. And so the question is it a sum over metrics? Is it a sum over metrics with a couple of strings on it? Is it a couple of metrics with strings and a bunch of brains? What is it?
I see.
And so, is there another way of getting the exact shape of the spectral form factor in Super Yang-Mills other than using the boundary theory?
Okay, and I guess Jan was asking what computation should we do in the boundary to answer those kind of questions?
Well, let's assume that we know the boundary. Let's say we have a very powerful quantum computer and I can draw the exact shape of the spectral form factor. So just I can give you that red curve. We sort of, that at least we know the equations to solve, even though we can't solve them. Is there another set of equations, well posed, that if you were powerful enough, another set that involved different variables that everybody in this quote unquote room would call a different dual description that produces exactly the same curve? And that's the question. And Daniel, do you want to say what? Right. Okay. Daniel, do you want to say your thing out loud?
Okay, yeah, so yes, that's the question, but the answer to that question is not what's meant by simple gravity. Simple gravity is the thing that that is the thing where the integral is just over the supergravity fields and,
right,
fixed up a little bit in some way that we don't exactly know how to characterize.
That's the question. The question is, how does that relate? Is that some, almost alpha state? Is that some sort of blurring? Is there some useful notion of being in between this mythical thing? Well, I don't know if it's mythical, this thing we don't have yet, and the thing we know how to compute with. Those are the questions.
Yeah.
Sandeep is Julian and Sandeep. I think Sandeep, I saw him first. Maybe Sandeep first and then Julian.
Yeah,
I just wanted to say something quickly to Steve, but then I wanted to come to my question, which is, Steve, let's assume that ADS-CFT extends to full closed string type 2B string field theory being equivalent to the boundary theory. Then you would have to do the computation of your ramp with all its intricate structure, presumably in type 2B closed string theory. And as Daniel said, it's not simple gravity, but presumably there you would get the same answer if the duality is correct.
Of course, that's right. The question is, what is that thing? What is string field theory? And that we don't know what it is.
Barton gave a great summary in which he said all string field theories have been constructed. I know nothing about the subject, but okay.
Well, yes, I agree. It's very interesting. It's not, I think dealing with black holes is not quite there yet. But that's right. That would be kind of along the line that and the question is there a way of kind of, approximating that theory in a way that looks a lot like metrics and wormholes for computing certain things? for instance, suppose you wanted to compute the time average spectral form factor. Could you see that that thing would produce wormholes?
Yeah.
And the question is, how does it do it?
Yeah.
And what's the first correction to a wormhole that that equation predicts? Those are the kinds of questions.
Yeah, yeah, I agree. Actually, that brings me to the question, if I can ask, which is, and Steve already maybe gave a partial answer to this, but Jan emphasized the fact that sometimes an ensemble average might arise from a theory which is, say, a single Hamiltonian theory, unitary theory, if we did coarse graining over energies, I think is what Jan was saying. But to my mind, and maybe it's a semantics distinction, but I'm not so sure, when I see the ramp with all its very intricate structure being roughly approximated by just the linear growth, isn't it more like a time average being reproduced, a coarse grain time average being reproduced by an ensemble average? And the reason I'm asking this is something we know very well happens in statistical mechanics. You have a closed system with a single Hamiltonian, and because it's ergodic with many degrees of freedom, you can reproduce coarse grain, simple correlators through an ensemble average. And maybe that's what's happening in cases where wormholes exist and give a good approximate description. Is this reasonable? The follow-up to this would be in the papers you folks have written, where you, for example, look at single instantiations of the SYK model. I'm sorry, I haven't fully studied them. What happens? You don't really have any effect connecting the two boundaries, but perhaps I think you see the wormhole being a good approximation anyway, perhaps because the time average is anyway well given through an ensemble average. Sorry. Just thought I'd get your comments on this.
Maybe you could combine with Julian and then get back to both of you.
Yeah, because I think I actually have a similar question, which I phrased slightly technically, was actually just a small clarification question. So Stephen, what is his opinion on this? When you say that it actually computes exactly the same, say, spectral form factor, do you mean that it really computes exactly the same points? Or do you mean that it is able to reproduce the exact statistics, so all of the moments?
I mean exactly the same points. That's that is the hope that many of us grew up on.
Well, no, but I mean,
okay. that there is a duality between CFT and ADS.
I won't try and tell you what your hope is, but I mean, being able to characterize just all the statistical properties of this thing would already be extremely, would be amazing, I think.
Granted.
All of the statistical properties, not just its mean and not just its variance and so on. So it's just a different, sample of the same statistical distribution.
Well, okay, I agree that there could be many middle places along the road that would be very interesting, but Juan, I think there was some comment about Juan's in the chat that might be relevant here.
Yeah, I think there are many discussions about most, from Juan,
So I guess there is the idea that perhaps type 2B superstring theory in 10 dimensions might not be a unique theory as we normally think it is, but might have an ensemble average. So one question we can ask is which is the first operator that varies from member to member in the ensemble?
Mm-hmm.
And there are some simple operators like the R to the fourth term and so on, which we think are completely fixed, as people have shown. And I guess what is the first one? Is just the first non-protected operator, non-supersymmetrically protected operator enough, or should we go to more and more complicated ones?
Sorry, let me maybe ask. I could not understand very. So, would you average over what? Over the string coupling? Over?
No, I think the idea is that even the theory for fixed string coupling would be dual to some ensemble, or there would be related to some kind of ensemble. And
I think what you're saying is
an ensemble which can't be eliminated by going to a super selection sector.
No, well, it's related to the super selection sector. So for example, in the philosophy that Henry was proposing, you would access this by forming a black hole and letting it evaporate. I guess you also proposed a similar thing with Polchinski. And the question is, well, that's in principle one proposal for a coupling or a process that would depend on which member in the ensemble you are in. But which is the simplest process? Is that, I mean, we know that if we scatter 4 gravitons and we look at the R to the 4th term, that is fixed. But is there some operator further down which is not fixed? And maybe we could try to see whether that is somehow fixed.
Maybe I'm confused by something basic, but those rules of fixing the terms, like we heard in the talk by Ashok and others, aren't they based on a more conventional theories where we don't average and so on?
Well, if you have a non-BPS operator, so if you have a BPS operator or some protected quantity, then you might think it does not fluctuate. It's fixed by some kinematics or something, like the R to the 4th term in supergravity. But if you take some other piece that's not protected, there's no reason for it to not be sensitive to some detailed super selection sector. And you could explore whether if you can try to find an argument whether it has fluctuate or not. And if that would be the first candidate operator that might fluctuate, I would guess. I guess that's what Juan was saying as well.
Yeah, but I think the instanton correction to d to the 8 R to the 4, for example, can be calculated in principle. Right? I think the Harvard group is already into it, and there doesn't seem to be any non-uniqueness in that calculation. Right? Just, the standard instanton if anything.
I guess I think if you think in terms of ensemble, you would think that the instanton should be a space-time instanton, some amplitude of order 1/G string squared, where you have a topology change of the full background space-time.
Well, it's asymptotically flat, right? I mean, it's localized in space and time. You are thinking in terms of some.
Well, those are, I mean, I think you're arguing that the effects of order 1 that go like e to the -1/G are fixed. But
yes,
I think people who would propose an ensemble would say that the effects should go like 1/G squared because they involve some kind of space-time instanton where you change the whole geometry of the closed string background.
I see. So those will be different kinds of instantons, not the ones that we.
Yeah, that's right. That's right. And yeah.
Well, I have a question I'd like to ask, since you just replied. Do you think string field theory in its current state of development could say something about black holes? I mean, in principle, I mean, not solving equations, but, is it computationally well enough specified to study high energy states?
No, I think certainly closed string field theory is not in a position to do that. Open string field theory, I think, is much better understood.
But suppose you just collide a couple of open strings, I don't know, and put it in ADS or something, do you think you could make a big black hole that's stable for a long time? Do you think by solving the equations?
Yeah, I don't know. It's worth trying. I mean, open string field theory, it's a well-defined object. Classical open string field theory is a well-defined object. You have standard mechanism for quantizing, the BV. And many classical solutions have been understood, right? So it's possible that by colliding.
But can you define the integration contours for the quantum theory? Can you, compute compute it? Is there a non-perturbative kind of even semi-formal definition that makes sense? That's not just summing over saddle points?
I think the D instantons or all Euclidean D branes are reasonably well defined.
Yeah, but beyond that, things that are...
beyond that, I don't know. Yeah, I don't know. Okay. Certainly, it's nothing has been done.
Okay, but that's interesting. There were some other questions that we got to. We have lots of people raised with raise their hands. I haven't kept track of who's first.
Yeah, let's go maybe with with Thomas.
Yeah, thanks. I just wanted to mention that the discussion is quite abstract. So if we go away from JT gravity, and since this is a strings conference, try to think of the higher dimensional examples, which Jan was mentioning. I was wondering what people actually have in mind. So are we talking, I mean, to make it less abstract, which wormholes are we really talking about? Do we always have in mind these constrained instantons? Or is it more like what Maldacena and Maus did? Or actually the original example by Coleman? Because it's Coleman who started this whole discussion about wormholes. And then at least the good thing of the Euclidean axion wormholes is that they are the operators that source them are actually, so the bulk fields are dual to marginal operators. And from the chat box discussion, it seems that people are willing to say that you can actually maybe create an ensemble of CFTs by averaging over the conformal manifold. Maybe that can make sense. So I'm wondering, what do people have in mind? I think you kind of need to specify, otherwise the discussion remains super abstract.
Yeah, can I say something? So my impression is that the rules of the game are not very precise. I think one thing that you can do is you define for yourself a low energy vector field theory that you work with, right? Because we don't have the power to construct these things in full string field theory. So you use your favorite low energy effective field theory and you decide what the rules are for you. And then with those rules, you can do a computation. And there may or may not be a wormhole according to the rules that you're using. And then you need to ask yourself whether that's an artifact of the rules that you're using, or whether you think whatever you were computing is reliable and gives some insight in the full theory.
But Jan, can you specify? If you tell me Euclidean supergravity, I know what to do.
That's a particular, well, if you can decide that that's the theory that you work with. For example, you could say I'm going to work in pure gravity or something, right? I'm ignoring everything else, but then that's, that's incredibly unreliable because you threw away lots of light matter fields and so on. You could also take like, some Kaluza-Klein reduction, or you can take 10D string theory or 10D supergravity on ADS5 cross S5. You can, I think you can pick your low energy vector field theory, try to do a computation and try to interpret it. But I don't think there is sharp rules at this point.
Okay.
Mihailo? Mihailo Kubrovic?
Jan had a question on the role of ensembles for Lorentzian wormholes, but you just glossed over it. So I would love to hear if you can comment on that. In particular, I mean, it seems that we normally interpret a Lorentzian traversable wormhole as dual to literally just two interacting subsystems, so no ensemble, literally two systems coupled. But then if it's non-traversable, then it's normally interpreted as a thermophile double. And we usually think of it not as two systems, but as a single system, just with the formal doubling of the degrees of freedom to account for the temperature. So could you comment on that? I mean, how to resolve that?
Oh, this was an invitation for someone to say something insightful, because obviously we have the usual thermophile double situation where if you want the Einstein-Rosen bridge, if you want to call that a Lorentzian wormhole, is connected to entanglement. So those things I think we understand quite well. My question was more, are there interesting Lorentzian computations that tell us something that we have not yet learned from Euclidean computations? And if so, what are those lessons? That was my question, and it was an invitation to everyone listening to say something useful about that question. I just wanted to raise the question. I don't have anything particularly insightful to offer myself.
Mm-hmm.
So
I think Andrea has a comment related to this.
Yeah, I think that the distinction between Euclidean and Lorentzian, I'm going to say this again until is not as sharp as perhaps it's suggested in many of these discussions. The replica wormholes for computing the page curve from a black hole formed from collapse are Lorentzian, or at least can be written in a language that is purely Lorentzian, makes no reference whatsoever to Euclidean. Yeah, there is another distinction, which is between spatial wormholes, things like the traversable wormholes and the Einstein-Rosen bridge, and space-time wormholes, which connect different complete boundary components. And that, I think, is a very important distinction. One is related to entanglement and one is related to ensembles. But the distinction between Euclidean and Lorentzian, I think, is not terribly important at a conceptual level.
Ben? Ben Fravagel?
Yeah, I just wanted to mention it's very interesting, averaging over theories. It seems very hard in higher dimensions. And I think an easier thing, especially in the ADS context, is averaging over states. Steve was asking the question about, a gravity calculation that could calculate this plateau. And I mean, we showed that like in the ADS CFT context, you can calculate basically the variance of that 2-point function, average over an ensemble of states. And then that becomes just a thermal field double calculation that's under control in semi-classical gravity. So basically averaging over states, brings these, it allows you to compute these variances kind of along the lines of what you were saying in your talk. And it's sort of more obvious that it makes sense to average over states in the higher dimensional case.
Do you think averaging over states will smooth out the time dependence in the spectral form factor?
Well, I mean, the thing that's under control is you need to average over states in some range of energies, and that averaging will smooth out that noise. So you can then ask about.
I don't see how it will, given that it doesn't change the energy eigenvalues at all. It just changes the size of the fluctuations, but it'll decrease the size of the signal, but I don't see why it'll change, why time 1 is different than time 2. That's all about the eigenvalues, and that's averaging over states doesn't change that.
But isn't it?
Sorry,
like
are you asking about whether
low-pass
the noise
filter?
will be smoothed out in this calculation?
Yeah, it's like a low-pass filter, depending on how you choose the window. I think it does kind of filter the signal a bit.
Well, maybe this is too technical. We should go offline. Okay, look, maybe we should reserve that, Ben.
Yeah. All right.
Okay, but so there are other people. I guess Andy Strominger hasn't had a chance, and he's been waiting a long time. Who else?
Alex Mellon.
Yeah, Alex said something earlier. Let's go to Andy and then Alex. Okay.
Sure.
Yeah. So this is a question. So what about the possibility, there doesn't seem to have been that much discussion of this, that either the model needs to be modified or the use of the Euclidean path integral needs to be modified, and in some way, I mean, Euclidean path integrals in quantum gravity are, of course, notoriously subtle, and that all this ensemble average is a symptom of having done the calculation wrong or starting with an inconsistent model, and that we need to modify something, and then we'll have a nice unitary quantum theory of gravity. Is that possible?
Yeah, I think maybe this is along the line of was it Douglas's first question or second question about what is there something you could add to quote unquote simple gravity that sort of fixes things up and where things factorize, and that seems plausible. This baby example that I talked about, where you take SYK, which is a completely well-defined path integral, whatever else it is, these auxiliary fields, you're just integrating over them. And in this toy example, this toy squared example, it's just an ordinary integral. And you find there's a wormhole that has all kinds of problems. It's just, it doesn't factorize and all, but there's this other part of the integration space, that's noisy and restores factorization. It's not clear quite what its geometrical interpretation, but that seems quite possible, that there's a way of doing the integral that gives wormholes plus something else. And that seems possible.
Okay, thanks.
Yeah.
Alex?
Yeah, so one comment or question, something that's not clear to me is, let's take the ensemble averaging hypothesis seriously for a second. And this is sort of related to Juan's question earlier. And we take, say, type 2B supergravity on ADS5 plus S5. And we want to say, okay, that's dual to an ensemble of CFTs. how we're going to make that precise, because we still need to be solving the bootstrap equations exactly, not approximately. So I don't see how we could ever land on anything else than maybe an average of n equals to 4 over the Toph coupling, because that is the set of data that solves the bootstrap equations non-perturbatively. So I'm not exactly sure how we could ever land on anything else.
Yeah, it's not even obvious for me that averaging over coupling, is it obvious that it's still a solution of the bootstrap? Ah, no, it is, of course.
I think so, because it's every single instance that you summed over satisfies crossing.
Yeah,
so
sorry, of course.
I think that works, but that, as far as I can see, that's the only thing that works. So if we really want to take this ensemble average seriously, what else could it be?
If you would input low energy information in the bootstrap, including all these error margins. Because as a low energy observer, everything we measure and everything we can compute has error margins. We don't know sharp low energy correlators, we know approximate low energy correlators, right? If you input imprecise information in the bootstrap, could the output not be something accurate?
So then what you're saying is you would violate the bootstrap conditions by exponentially small effects. You're going to allow yourself to violate the bootstrap axioms by exponentially small effects.
Putting, the only thing I know is I have uncertain information to begin with. There's some error margins, and now I'm running the bootstrap program. What is the thing that I get?
I have a suggestion. Let's close here the official part of the informal discussion by thanking very much Douglas, Jan, and Steve for a beautiful discussion. And we can unofficially continue for 10 more minutes. And but the official part, the one for YouTube, I guess we can close it here.
Can I get the instruction on how to go to poster session?
So I think for poster sessions, we will create breakout rooms, and then you should just click on the breakout room and choose the room. Okay, so
also we come back to this
are you
Zoom
there?
link.
It will be on this Zoom meeting, and we will put a page on the screen with the various rooms and the names of people. And people will just be able to click on the button that says breakout rooms and choose which room they want to go to. There can be 6 people at each room, and you can just move around in the various rooms, including people that are giving the posters. They can also move to other rooms to check other posters and then come back when they see someone in their room. So you can see who is in the various rooms, and we will have 50 rooms. So, yeah.
Thank you.
Maybe I can make a comment related to Alex's question just now. I feel like the state of the art in terms of our understanding of the bulk theory dual to n equals 4 super Young mills is not enough to describe exactly n equals 4 super Young mills. So when we talk about the bulk theory, we shouldn't be trying to get an answer that exactly solves the bootstrap. I think what our current understanding of the bulk theory is good enough to do is good enough to compute boundary observables that are consistent with some kind of formal ensemble, which is similar to n equals 4 super Young mills. And it's not completely well defined. So we shouldn't try to compare it to the exact bootstrap equations. In order to do that, we need to understand the bulk theory better.
Yeah, I completely agree. But that in some sense then says that we're not trying to make very sharp the notion. So we have a very sharp notion of saying, go from the CFT, which is non-perturbatively defined n equals to 4. And that predicts what we should, every single thing we should compute in the bulk. We may not be capable of doing that, and we don't really know the rules, but that direction is well defined. But the other direction seems very murky. And so it's not clear to me that you could ever try to make precise what you mean by semi-classical gravity is dual to something else. Like that direction of the arrow seems blurry at best to me.
Yes.
I think Henry and Tom and Mark wanted to comment.
Yeah, I guess I was just wondering, I mean, with maximal supersymmetry, it seems so. I guess the idea is that there could be some simple version of type 2B string theory, which is not which is the thing that would be dual to whatever ensemble we have in mind. But maybe someone that is an expert on these just constraining effective actions with maximal supersymmetry could comment. I mean, it seems like there's not much freedom, or is the idea that the simple version would have less symmetry somehow?
Is it possible there's an ambiguity in the large N limit? Some subtle differences in how you take it?
Maybe a related question is, there are many localization results, say, that are computed for any n, and can we use them to test some of these ideas?
Well, maybe a comment about that is that often these are used to compute things like indices, like the BPS index or something like that. And that's, I think, sort of precisely where we don't want to look, because those are very special states. And we're really trying to ask about quantum chaos and sort of the generic states. And so it might be very tricky to look along the axis of things like, you know, an elliptic genus or something that counts BPS states.
Let me make a comment, just since it's a discussion, it's informal and you're not being recorded, that just as an example of a fantasy you might have. You know, as people know, an example of a given fixed beautiful system like super Yang-Mills is the Riemann zeta function. And the zeros of the Riemann zeta function are in some sense analogous to energy eigenvalues. And they're just numbers that you can compute. They're once and for all, like super Yang-Mills energy levels. And there's this completely other way of computing the Riemann zeta function. Well, it's actually the only way, which, you know, by summing over primes or taking the product over primes. But there's something like wormholes in these semi-classical chaos things, which is, Montgomery showed that there's a ramp in the statistical distribution of the zeros. They look like random matrix theory. And the style of argument is very much like coarse graining and getting what's called the diagonal approximation. That looks like a wormhole. But I think maybe Douglas had mentioned the idea of an approximate solution of the bootstrap in some informal discussion, and I just decided to go cruising the literature. It turns out some proof techniques that mathematicians use to prove things about the statistical distribution of zeros involves the notion of constructing approximate solutions to the functional equation that the Riemann zeta function obeys, which is the analog of modular invariance. It's part of a bootstrap thing. And they look for approximate solutions and families of approximate solutions, and then they average over them. And they use this to try to establish precise results about the kinds of statistical things that we're talking about, products of partition functions, or maybe products of maybe spectral determinants in our language. But so this notion is not, it's not just, crazy. Well, maybe it's crazy, but at least in some rather well-posed example, it's led to precise results. And I'll try to dig up a reference, and I'll put it in the chat.
I was going to ask.
Yeah. I spent a little time with a student trying to make sense of it. I couldn't, but I'm not the right person to do it.
But as long as you don't say you're working on the Riemann hypothesis, it's okay.
Yeah, I am not saying that. Okay, yeah, I'll put a reference in the chat. Maybe right. Maybe I don't know where the interchange will go. All right, I'll put it.
Maybe you had many comments in the chat. Maybe it would be nice to.
Yeah, I wanted to comment on. Actually, Douglas was mentioning this earlier. I want to sharpen kind of the question of what is it that we want to compute from the bulk to pin down equals for supremos, let's say. And I think we should separate things that are that we know we can currently get explicit answer for versus things that can in principle be calculated in the sense that we have an algorithm for. And I would say that, so from bootstrap perspective, we think that if we can pin down the list of operator scaling dimension, of operators in equals for supremals, then the theory will be completely determined. And that data, for instance, in principle from the bulk, we think there are all the ingredients to do a complete series expansion in 1/n, at least perturbably in 1/n, but to all others, because that's in principle determined by perturbably flow string field theory, if you wish. Of course, in practice, it's still a very tough problem, but in principle, the algorithm is all there, just a matter of computational power. So to me, the question is, from this perspective, given what we know about the way we define type 2D string theory in ADS 5 the question really is, how do you go beyond the perturbative series in 1/n? And then there are we can discuss e to the minus n effects and e to the minus n squared effects. So I think one can kind of corner down our ignorance to specific non-perturbative corrections in 1/n I would like to pin down. I'm not saying that that part can be determined from what we know about the bulk, but I think the question can be sharpened.
I think Andre has a comment precisely related to this, it seems.
Yeah, and related to this discussion. I mean, if we suppose we were all powerful and could do what G suggests and compute everything we wanted order by order in an asymptotic expansion in 1/n, plus including some instance-on corrections if we wanted, but all we have access to is this asymptotic expansion plus instance-on corrections, then if we wanted to compute something like a spectral form factor, which we expect to depend, I think, very erratically on n, what's the best that we could hope for if we only have access to an asymptotic expansion? I don't really know what the answer to that question is, but the answer might be the asymptotic expansion gives us an excellent approximation to statistics instead.
Alex?
But the procedure you're proposing, she would not allow us to compute the scaling dimensions of operator of order n squared, right? They would enable us to compute the scaling dimension of all operators whose conformal dimension is fixed in the large n limit, I think. Do you agree?
Yeah, I agree. A priori, yes. I agree with that.
And this is really what we're asking about. So I don't know how this relates to Henry's question. I don't know if you know,
Well, okay, but sorry, I actually would turn this around slightly because it depends on how accurately you can determine the operator of dimension of order 1. Okay, I mean, in principle, we will believe that if you can pin down, to arbitrary accuracy for n equals 5, we will be able to bootstrap everything given that data. We're ignorant both about operator spectrum at dimension order n squared, as well as various small corrections to operators of dimension 1. I'm not sure which one is the best thing to tackle from the bulk perspective, but I'm saying,
right.
But wouldn't you have to know, the contribution of virtual heavy pairs of black holes to matrix elements of light operators to?
Yes, but that's not in contradiction with what I'm saying, because indeed we do not know how to, or at least there's no algorithm to determine e to the minus n squared or the correction to the Konishi operator scaling dimension.
Right. So yeah, I mean, right. So yes, it's true. It will infect low dimension operators, but by very small amounts that seem hard to compute.
Right. From the bootstrap perspective, in trying to solve conformal data of a CFT, let's say a given value of n equals 3 or something. In practice, that is the kind of approach. We do try to determine the low lying operator dimension as accurately as possible. And it doesn't give you everything, but it gives you a lot, and and if you make it arbitrarily precise, we believe that you will pin down the theory eventually. So it may not be the most efficient way to access the data you want,
I would suggest that we could continue on Slack. I think it will be fun to have more discussion there and further suggestions on how to proceed. But right now we have to test the breakout rooms. So let's please thank once again Douglas, Steve, and Jan for the formal and the informal part of the informal discussion. And let's set up the posters, and please check out the very many posters.
Right. Thanks to you, Pedro, for doing such a good job.
You did everything. Okay. Nathan, I'll pass it
very
over.
good. So I'm just going to put a share screen with all the different breakout rooms, and I'll open the 50 breakout rooms, and you guys can go wherever you want. I'm also going to allow